Good morning, ladies and gentlemen. I am Jude Mohammed, and welcome back to the second day of the Future of Semiconductors event. We are happy to see you, and I am incredibly honored to be here today. Starting off this morning with a plenary talk on the high efficiency GaN-based electronics for RF and power conversion, the next hyper-growth phase for GaN. He received his PhD from Cornell University. He co-founded the first startup in the world of commercialization, RF, GaN, transistors, and LEDs. He received the ISCS Young Scientist Award, the Welker Medal, and the ISCS Quantum Device Award. Please welcome Professor Amesh Mushra.
Oh. Hello. Salam alaikum. And greetings to all. Thank you very much for inviting me. This is a great honor to be here today. And hopefully what I have to say will be of interest to the audience. Let me just see, where is the, okay. Forward this somehow. Huh? The green button. Is that right? Beautiful, okay. So why is GaN the preferred next generation semiconductor alongside silicon? There are many reasons why semiconductor technologies become important. One is that it has to be high performance. And it, of course, based on application. What is high performance is determined by the application at hand. It has to be very reliable, okay? Any semiconductor, this is not only GaN. It has to have a roadmap for lower cost with every generation. This is the gospel or the actual the mantra that we use for semiconductors. If you do not have a lower cost with every generation, semiconductor technologies die. And low cost requires very wide market penetration. So a niche technology is okay, but it'll remain niche. And then gallium nitride, more than any other semiconductor, satisfies all these requirements. Photonics applications, LED and lasers, we heard from Shuji and Steve yesterday and others. Electronic applications from kilohertz to terahertz, I'll explain what that means. Kilohertz refers to power conversion applications, and up to terahertz refers to communications. Wireless base stations, radar, millimeter wave communications, BAW filters in cell phones, all this are transitioning to gallium nitride. Sensing applications in the UV, chemical sensors, et cetera, and extreme electronics at high temperatures, oil drilling, and jet engine control, and so on and so forth. So if you look at gallium nitride, it has an enormous swath of applications that it can address, and that will allow it to actually reduce its cost going forward. So why is GaN so remarkable, right? So GaN is a direct bandgap material, and it emits light from a dislocated material. No other material really does this. You can detect light, you can make solar cells from polycrystalline materials like cat telluride, but you can't emit light from materials that are dislocated except GaN. Okay, so it's the basis of a greater than $10 billion industry, and who would have thought that, right? GaN is a wide bandgap solution for not next generation, it's actually current generation base stations, and it's been chosen over dislocation-free silicon carbide MESFETs. And nobody would have thought that. I remember in conferences 25 years ago where I was the sole person arguing for, I was trying to be, in fact, I joked once in a Japanese conference that I feel like I'm the messiah of gallium nitride, because, and with no followers. I mean, it looked like the life of Brian, actually. But anyway, and the other thing that was very interesting is that if you look at gallium nitride, let me see. This thing was working great until I came on stage. Okay, whatever. If you look at dislocations in gallium nitride, they don't move after they've been formed. The nice thing about dislocations that don't move, you can design around them. It's only a varying dislocation is what creates it's a real problem, okay? Because you can't design around something that's varying all the time. So it's bad, but it's fixed. And that you can always deal with that. Yeah. And there's no shear stress in the C plane of gallium nitride as grown. So you end up in a situation where these dislocations don't move, okay? So I call gallium nitride also a future-proof semiconductor. I mean, there are many choices in life, and you got to bet on something. So, I bet on GaN. Why? Because the future-proofness, if you want to call it that, of gallium nitride comes from the fact that it has multiple applications. I'm kind of overstating this fact. Solid-state lighting, we heard a lot about that. Shuji, the creator of it. Airborne radar, all airborne radar for military applications switching to GaN. Data center power supplies are switching to GaN. The European Union now has the titanium standard that will kick in from 2026. It's impossible to reach those standards without using some form of gallium nitride in the power supply. Compact chargers, they're flooding the market now for Apple, Xiaomi, and all these other phone makers. 5G base stations, that's a picture I stole from NXP. All 5G base stations are switching to gallium nitride because you can't get the bandwidth. You can't serve as many customers in 5G if you don't go to GaN. Home energy systems. This is an ensemble from Enphase. It's what I show you. I'm cheating. That's not made out of GaN. That's made out of silicon. But they're switching to GaN. This is public knowledge. And the reason is that any battery system converting DC to AC, you don't want to waste that in the converter, right? So the GaN is a great place there. And then if you look at electric car, the electric car, there are many aspects of the electric car. The DC auxiliary inverter, this is basically using the car battery as your mobile power source, converting the DC of the battery to AC for use when you go camping or under disaster conditions when you lose power and your car becomes your local power supply. And then, of course, there's onboard chargers and so on and so forth, and then the EV powertrain. The EV powertrain today is the domain of silicon IGBTs, a form of silicon transistor, and silicon carbide. Gallium nitride does not play a role there, and it is my remaining life's goal to actually put gallium nitride in an EV inverter. I hope I live a long time because it's going to be a hard thing to do. But the nice thing about gallium nitride, and thanks to Shuji and Steve and colleagues in the photonics domain, the LED industry has shown that gallium nitride has been the most rapid. Let me just read it because I'm going to botch it. The rapid adoption of LEDs in lighting marks one of the fastest technology shifts in human history. And the reason for that is that the cost of the LED dropped. And on the y-axis, you have LED price of dollars per kilolumen. It started up in $100. Now it's sub-dollar, right? So you basically have a technology that is inherently able to drive the cost down. And remember, semiconductor technologies, you've got to drive the cost down. We are the only, we are the only technology in the world, only product in the world that actually promises the customer that I'm going to reduce the cost. You can't get a hamburger, which you go to Burger King or someplace and they say, don't worry, tomorrow is going to be cheaper. Never happens. But we do, and we are supposed to make a profit out of that. Anyway, but we do. And that's the amazing thing of semiconductors. So this driving the cost down is amazing, right? So that's what we can do, and LEDs have shown. So let's first talk about power conversion. Electronics without waste. Okay, so if you look at, I keep driving this concept of cost and performance. If you look at, that's a picture of James Watt, who we have assigned the invention of the steam engine. But the steam engine actually existed before James Watt. But it was expensive. And by the way, the steam engine was used in mining, and it was expensive. What did James Watt do? He basically got together with a guy called Matthew Boulton, who's the capitalist, he's the money guy, and the two of them decided to make a more efficient and low-cost steam engine. And it's the fact and that became useful. So James Watt, therefore, becomes the inventor of the steam engine because he makes the more useful steam engine. And so the reason I like to show this is as engineers, we have to think about cost and performance. We just can't think about performance alone. It makes no sense, and the world doesn't reward you. So we are paying a hidden tax on electricity, and the problem is the answer, right? What is the problem, actually? And the reason is that most of 10% of the electricity that is generated is lost in the conversion of electricity from the form in which it is delivered. So it's basically AC at 230 volts or AC at 110 volts. And then it's converted to DC, say, for example, to power our laptops or whatever else, right? So there's a lot of AC to DC conversion. That's an example. And if you sum up all these conversions, there's about a $40 billion hit that we are paying. Now, this is a hidden tax, right? So when you pay the utility company, then what you're paying for is not only electricity, but also heat, because some of the electricity you use is actually wasted as heat. $40 billion, that's a lot of money, right? And that's, I have to show this because this is the way you get money in the US, is 318 coal power plant equivalents of electricity. That much of energy generated is just lost in power conversion, okay? Power conversion is inefficient. So when you have a power switch, we actually have a very efficient power switch, and that's the switch on the wall, okay, on the left. That is a very efficient switch. It's open when it's off, and two metals touch when it's on. So when it's off, there is no leakage. It's completely off. And when it's on, there is very little loss in power because there's two metals touching each other. The problem with this is it's dumb. Okay? You either turn it off or on. If you want to convert the power, you have to switch it on and off in a form. You've got to actually do what's called pulse width modulation. You basically have to convert electricity and modulate it by doing this modulation scheme. To do that, you've got to switch the device on and off fast. And even graduate students who are willing to do almost anything refuse to do that. So you need a switch that can actually switch at a megahertz, kilohertz or megahertz, which allows you to shape the form of energy coming out. That switch, therefore, actually, the fact of you're turning it on and off is a loss in power. You're charging and discharging capacitors. That's called switching loss. And when the device is on, you have the resistance of the semiconductor, which makes it lossy, okay? So you want an ideal insulator on the left, an ideal conductor on the top right, but what you get is basically what's at the bottom right, which is a semiconductor which you want to drive to the star. You want to have very low on resistance when it's on, and completely a very high breakdown voltage or very high standoff voltage when it's off. So gallium nitride, which you see out there, there is a gallium oxide that people are looking at now, but I like gallium nitride because it has got these, it's great for power conversion and it's wonderful for a lot of other things. There are two forms of gallium nitride. One is called gallium polar, the other is called nitrogen polar. Gallium nitride is a wurtzite crystal, and if you look down on the common form of gallium nitride, say an LED, you'll see a layer of gallium atoms, okay, and that's called gallium polar. If you flip it around, you get nitrogen polar, and if you look down on the crystal, you'll see a layer of nitrogen atoms. Both these forms of gallium nitride are very useful in electronics. Nitrogen polar, not so much in optoelectronics, extremely useful in electronics, because you can make what are called high electron mobility transistors, where if you put aluminum gallium nitride on gallium nitride, the red on the purple, in gallium polar, you get a two-dimensional electron gas, which is a dotted line. Those are electrons, okay? And In the gallium polar case, you have algan on top of GaN. It looks more like a MOSFET, where the oxide could be the aluminum gallium nitride. In nitrogen polar, you have the algan below the GaN. That means the two-dimensional electron gas is sitting on the wide bandgap material or the quote-unquote insulator, right? And that's called an inverted transistor, nitrogen polar transistor. Both these are amazing, and I'll talk to them. How do we make this transistor? Much like a MOSFET, a source and a drain, and a gate, which controls the flow of current. And if you guys want to think of it this way, in your mind's eye, just remove algan and put in silicon dioxide, and it'll look like a transistor to you. And the reason why gallium nitride is so good is because it's, let's call it a MOSFET with a channel mobility of 2,200. 2,200. I mean, God was having a good day when he invented gallium nitride, because he gave you a material, or she, I don't know, he, whatever, gave you a material which was high band gap, so it could hold voltage. So it was almost like an insulator, but it had electrons with mobility to die for. Okay, 2,000 mobility is very high. It's a compound semiconductor mobility with an insulating band gap. Phenomenal, okay? So that's why I love this material system. The opportunities for gallium nitride start from the kilohertz all the way to the terahertz. And let me talk about first power conversion. If you look, if power is lost, and I told you in the form of converting power from one form to the other, okay? So if you look at industrial motor drives, you convert power of one form at 230 volts, and you actually get power out again at 230 volts. But the reason you call this power conversion is basically if you have a variable speed drive, if you have a motor, and you want to change the speed of the motor, what you do is you get 230 volts in, you get 230 volts out, but you can control that 230 volts to change the speed of the motor, for example. So variable speed drives fall into this category, right? And if industries use most of the power, okay, people at computers don't, all right? Industries, where you move stuff, conveyor belts, you know, steel plants, oil wells, I mean, they consume power. So that's 207 terawatt hours you've wasted. Data saver power supplies about 52 terawatt hours and growing. Solar inverters growing 1.6 terawatt hours, and automotive inverters 13 terawatt hours and growing. So the question is, how much is a terawatt hour? Because you say terawatt hour, and you say, what the hell is a terawatt hour? You know? And a terawatt hour is, San Francisco consumes 6 terawatt hours a year annually. New York City, 50 terawatt hours. Vegas, 33 terawatt hours. One street in Vegas, right? And the reason is why? It's not the lighting, because thanks to Shuji, the damn lights don't take any power. What ends up happening is air conditioning and all this other stuff. Motors, blowing air. It's a very power-hungry thing. So what you want to do is you want to actually minimize power conversion losses. The saving potential of gallium nitride is over 300 terawatt hours, which means the entire west coast of the United States, where people are only on computers, they don't do anything, right? So they're all on computers. They don't use a lot of power compared to the Midwest, where we make stuff. So on the West, you consume 300 terawatt hours of electricity, and all the electricity in the West Coast could be provided if we didn't waste energy. You could take it off the grid effectively. So this is an enormous problem, and it has to be addressed. It's not sexy. It's not a very, you can't go and like impress your partner by saying, oh, I'm working on power conversion. It doesn't work. However, power conversion is the most cool problem to work on, eliminating that heat, okay? So there's a Moore's law of power conversion. That is, just like in electronics, right? In Moore's law, you keep making you make things dense, more and more dense. And the way you get more density and more chips per centimeter square is by reducing the gate length of the transistor. That's called gate length shrinkage. That's what industry has been doing for the last 40 years. In power conversion, we also have, quote unquote, a Moore's law, but the way you make things, the way you make things, what is goodness in power conversion is how much power can you convert per centimeter cube. That means how small can you make some stuff? How much power can you convert per centimeter cube? That's power density. So the metric for us is power density. So as you go up from the bottom left to the right, you get more and more, you get smaller power conversion units that can convert more power. Okay. So you go from like bipolar transistors, IGBTs, silicon superjunction, silicon carbide, and GaN. So there are mega markets driving growth of GaN. The smartphone, that's tablets, laptops, gaming consoles, crypto mining, electric vehicles, that's on the power conversion side. And on the 5G RF side, there's infrastructure. This is communications. It's going to 6G now, not now, but will go. And then there's a Department of Defense or Ministry of Defense, I don't know, in the kingdom, what you call it, but the DoD in the US, which basically is in radar applications and so on and so forth, and then you have commercial applications. So to make gallium nitride, and this is, I think, applies to the Vision 2030 that's here in the kingdom, you got to control the supply chain. If you don't control the supply chain, you can't innovate at all stages. That's the most important thing. So you can't just buy epi from someplace and do something because you lose control of innovation. So I transformed the company that I started a while back, too long ago, and you basically, you have to have you got to make the FETs, you got to make epi, fab, you got to design applications, and then you got to serve the market. Because there's innovation that happens at every part of the supply chain. All right. You also, if you want to make a technology, you got to actually make it broadband. That means you got to serve as much of the product portfolio as you possibly can. Because customers like to do one-stop shopping. So what they want to do is, if you decide, if your purchasing officer decides to go and I want to buy some power electronic devices for my company, they would like to go to one supplier and work out a deal for as many power conversion parts, because then you can get a good price for high volume. So if purchasing people don't like to go here to buy this, here to buy this, here to buy that. It just makes no business sense. So if you want to actually compete, you got to have a broad portfolio. Silicon carbide does. They work at 650, they work at 1200, they work at 1700. Gallium nitride works at 650 and now recently 1200. It has to be very reliable. So here's gallium nitride is reliable. The number of devices that have failed per billion hours of operation is 0.3. And it has a huge application space. Right from wall plug adapters, on the left is a wall plug adapter. In the future, every wall plug is going to be removed and be replaced by a plug that gives you electricity, AC, and also 2 USB-C outputs. So every outlet will have both an AC output and a DC output. That means every outlet will have now a power conversion source behind it. These are huge markets. You can imagine the markets that you're dealing with everywhere. Servo motor drives, computing, and so on and so forth. And this one basically says that gallium nitride, if you compare it relative to silicon carbide, performs better. This is to be expected. Physics tells you that gallium nitride is a better semiconductor for power conversion. I'm not saying that it's the better semiconductor in the market today. I'm not trying to get into a fight with the silicon carbide folks. All I'm saying is physics tells us that, and you should actually end up with a transistor that performs better, and it does. Now, whether it's more useful in the marketplace determines on business, okay? And its supply and all this other kind of stuff. But right now, This is extremely important to benchmark against current technology. And it's also cheap in the marketplace. Why? Because when you go to gallium nitride, you can take a traditional architecture of converting AC to DC, which is on the left, which typically there's an AC power source, there's a bridge rectifier that converts it to a half wave, and then you put the half wave through a low-pass filter, and you get DC. That's how we typically get AC to DC conversion. On the right is what is called, extreme right, is called a gallium nitride-based totem pole, which goes directly from AC to DC without a bridge rectifier. What is the consequence of that? You get very high efficiency, from 98% to 99%. Now, you might tell me, Umesh, what the heck is that? You're sitting out here wasting my time. You're telling me you're going from 98% to 99%. It's going from good to good, right? What's the difference? The difference is you're cutting half the loss. 98% is 2% loss. When you remove that loss by 1%, you're cutting the loss by 50%. Now, this is not semantics, because the actual loss is what I showed you, right? And if you cut that loss by half, that's a huge win. So 98 to 99% is a 1% gain in efficiency and a 50% reduction in loss. And it's important to think in those terms. Here's a company called Corsair. They make gaming power supplies that has GaN inside. And the reason you can go from this complex silicon-based structure to GaN allows them to make a power supply which is smaller. The right-hand side is a silicon-based power supply. Left-hand side is gallium nitride-based. You get a smaller power supply. Power density is going up, more power conversion per centimeter cube, at the same price. This is the price that you get on Amazon. And why is that? Because you can replace all these junky things like the bridge rectifier, some filters, EMI filters. You can remove all these things that cost money and then give the money to me, okay, for gallium nitride. But it's a fair trade because the customer gets less cost, okay? Yaskawa-san, we have a great relationship. It's one of the biggest it is the largest servo and inverter company in the world. And we are working with them to integrate servo motors with amplifiers all in one. And what that does is allows you to free up the factory. This is called Factory 2.0, where instead of cables running to factories, by integrating power conversion and the motor, you can, by wireless control robots. And this is a new factory floor being designed by Yaskawa and 5 minutes? Okay. Yeah. GaN in electric vehicles I've talked about that, and so we will skip this. Let's talk about RF. RF is huge, okay, because you have many applications. So you have radar systems, SATCOM, telecom, and military communications, right? Algan GaN HEMTs had this great history where you started with low output power and suddenly it took off, much like a laser, okay? So you have like spontaneous emission, which is basically progress that happens and then you get resonance. You get basically all the things, the ecosystem is in resonance, and then the technology takes off, okay? So we basically went from 1 watt per millimeter, the first demonstration at UCSB, the first demonstration in the world that happened at UCSB, of microwave power from GaN up to 40 watts per millimeter, which is an enormous power density. This is X-band, okay? And why is it good for communication systems? Because gallium nitride also has high linearity. So you can actually put many on the right. I show you arrows which can be customers all jammed together in a bandwidth. So you can serve more customers per bandwidth using GaN compared to other materials which have poor linearity, and your signal gets distorted. So you've got to separate the customers out further. And so you get less money per hertz, okay? And that's not good. RF GaN market is 700 million in 2019, going to 2 billion in 2025. And the nice thing about it is that it's now got a good balance between defense in the orange and blue is the commercial. So it's a good mix of DoD and commercial. Millimeter wave applications are coming. E-band radio, Atif had talked about it from CAST yesterday. E-band radio is 75 gigahertz, that's backhaul communications, communicating building to building. 77 gigahertz, 79 gigahertz is automotive radar. These are big markets, all just starting. It just is the beginning of this. Now, when you go to very high power density, like 94 gigahertz, this is very important for 6G communications, for millimeter wave radar on missiles or whatever else. You need an array to give you power, but at 94 gigahertz, the spacing between each element, which is determined by the wavelength, becomes very small. If the spacing becomes very small, if you don't want a humongous radar at the tip of your missile or wherever in your back pocket, if you don't want a big radar, you got to make these, the power density, the amount of power you can get out of each one of these, high. So watts per millimeter becomes hugely important at millimeter wave frequencies because of size constraints. And nitrogen and gallium polar GaN was stuck at 2 watts per millimeter beyond 35 gigahertz, 40 gigahertz. Nitrogen polar GaN, which is this flipped form of gallium nitride that we developed. So you have gallium polar, which is on the right, on the top, nitrogen polar is on the left. And when nitrogen polar GaN, this breakthrough we developed at UCSB, made us go from 2 watts per millimeter to 8.8 watts per millimeter at 84 gigahertz, 94 gigahertz. What does that have? What did we do to do that? Many things. Regrown gallium nitride for source and drain contacts, a GaN cap, a recess, and the GaN cap reduces dispersion and by reverse polarization enhances the channel conductivity of gallium nitride, making it a highly conductive channel while maintaining the breakdown of the device through the structure. I don't have time to go into the details, but I'm happy to talk about it after the talk. But we developed this whole new structure, but it is a co-designed structure, which is a lot of materials growth and devices. So I'd like to just end by saying that nitrogen polar gallium nitride has taken millimeter wave performance to numbers unheard of to this day. 35% power added efficiency at 5.3 watts per millimeter and 8.8 watts per millimeter with 27% power added, 27% power added efficiency. So nitrogen polar GaN is a new form of GaN that covers the spectrum all the way from S-band to W-band and D-band. Covers the whole millimeter wave spectrum, one transistor that can serve the full spectrum. And I'll just leave the conclusions. The conclusions are the same as my introduction, which is gallium nitride has a tremendous potential, not only because what it can do for one part of the market, but for the broad market. Thank you for your attention.
Thank you, Dr. Ramesh. With the session chair, please welcome Dr. Abdullah Al-Harbi.
Start with the question from the audience. Okay, go ahead.
Okay.
Okay.
Yeah.
So,
Thank you.
Okay. The mic, please.
Hello. Thanks for the nice presentation. Just wanted to ask if you can comment in maybe 2 or 3 points. First of all, is there any like limitations or power limitations using gallium nitride for like high current consumption or very high voltage like in power plants? Then the second thing is that the cost, as you showed the example for the power converter in Amazon, which uses silicon and which uses gallium nitride, they appear to us in the screen as the same price. But we didn't notice any price difference as like customers. But maybe the company is cheating us. We are not sure. The third point is that, like in the future, like your estimation is like to reduce, for example, the sizes for autonomous vehicles, radars. Like up to what size we can shrink the size of these small radars? Thanks.
Yeah, thank you for all 3 questions. The first one is the voltage for grid applications that can go up to 10 kV or 20 kV. Gallium nitride at the present time is not particularly suited for that at the moment. And that market is not being served by anything other than silicon at the moment. And silicon carbide can serve it, and gallium nitride can serve markets up to, say, today, up to, say, 3 kilovolts. 3. For 30 kilovolts, I think those markets are much more in the domain of silicon carbide at the moment. But vertical gallium nitride devices are being pursued today to try to address those numbers of 20 and 30 kilovolts. Lateral devices that I've shown in the presentation today are limited to about 1.7 kV to 3 kV maximum. Number 2, about the cost being the same. Yes, indeed, the cost was the same, but what they were giving you was more power. So one was 1500 watts was the power supply. The other was 1600 watts. So you were getting more watts per dollar, and it was a smaller box, which was also more efficient. So what the customer was buying was higher performance at the same cost. So there was a benefit for the customer. Okay. Now the third question that you were asked was about how small can you make radar, and that's actually a very, very big advantage of gallium nitride. In fact, if you look at the way people are looking at in drones, in UAVs, and in even ships, the reason why gallium nitride has replaced gallium arsenide is because it gives you more power at higher efficiency. So in the ship, the biggest advantage has been that the cooling system has been reduced. And that's very, very big. And the second thing is that the aperture of the antenna has become smaller. So the ship becomes less observable to the enemy. So and then for the 5G communications, if you can call it radar, it's not radar, but it's a transmitter, it's also much smaller and cooler. So if you ask me how small that has been, it's been a 30% reduction in the case of radar, and I'm not sure about the actual size reduction in the case of 5G. Okay.
Thank you. Okay, please. The mic.
Thank you, Professor, for the amazing talk. I have one question in terms of the nitrogen power HAMD. I'm wondering that the better performance of nitrogen power HAMD compared with the gallium power, is that mainly because of the, let's say, a better carrier confinement due to the device design, or because of the, let's say, high electromobility due to the material property?
Okay, so the answer is both. It's carrier confinement, so the electrons are basically prevented from going away from the gate, going into the buffer, because of the aluminum gallium nitride barrier. So that's a good thing, number one. Number two, it's not higher mobility, it's higher mobility at high charge density. So we basically have a very low resistance in the channel. So you have charge density, which is 1.2 times 10 to the 13th per centimeter square. Mobility is about 2,000. And this combination is it's impossible to achieve in gallium polar HEMTs. So we get much more, it's a much lower resistive channel, not higher mobility than GaN, gallium polar GaN, a higher combination of charge times mobility.
Thank you, Professor Michel.
Yeah.
Please, the mic is there. So maybe one more question.
Professor Mishra, thank you for the very informative talk. I have a question regarding this gallium nitride-based CMOS, the MOS technology. Just now you showed. I think what you showed is a MOS type of structure. Because in silicon CMOS, normally we have an inversion. We have to turn on the inversion to apply certain voltage on the gate. So basically, you make the, for example, it's NMOS, you have to make a P substrate into an N. So when this inversion occurs, so the current gets conducted. So in gallium nitride, this kind of CMOS-based device, do you also need to implant, for example, to just now in the device you show the structure to do some implantation to achieve those kind of N or P type kind of doping? But in CMOS, it's very in silicon device, it's very complicated because you have a very comprehensive doping scheme to achieve that.
Yeah, it's a good question. So I hope I did not convey the wrong impression. What we are not, let me tell you what we are not doing. We do not do CMOS in gallium nitride. We are doing NMOS only, okay? And it is normally on NMOS. So it's actually the device under normal circumstances at zero bias on the gate conducts current. And to turn it off, you have to apply a reverse bias. So it's a normally on NMOS. It's the thing that silicon people hate, right? But we love it because it's an analog. We are not using it for digital. We are using it for analog. And in analog applications, you're allowed to have a normally on device which is turned off by a negative bias.
Okay, thank you very much. Then another question related to that is, what's your operating voltage for in this case? Maybe let's say compared to silicon device, which is technology, let's say 65 nanometer, 45 nanometer, or this.
Exactly. So in silicon, if you want to do RF, I see Abdullah is getting upset. We're running out of time. Okay. But okay, I don't know. I'm just kidding. If you have in the case of 65 nanometer, you're talking about 3 volts or something like this as breakdown voltage. The gallium nitride devices that I showed you have a breakdown voltage of 50 volts, and the bias voltage is 20 volts. Yeah.
Okay. Yeah, that's true. We are running from time, but I'm not upset. So,
I'm just joking.
So, just quick question, actually, to close this sessions. So, what is the challenge you are facing to put gallium nitride in EV? What are the challenges?
In EV?
Yeah.
So, I think that one is, I'll start from the least challenging to the most. The least challenging is in the inverter applications. So everything below 10 kilowatts, I think gallium nitride has a very good chance to displace silicon carbide. This includes onboard chargers, I wouldn't say less than 10, even less than 22 kilowatts. Onboard chargers, DC to DC converters, and AC inverters, onboard inverters. I think gallium nitride can get in there and beat silicon carbide. Where we'll compete head to head, and I hope we win, but inshallah, as you say. But we have to try our best, and that is in the EV inverter. And in the EV inverter, silicon carbide is doing well, and it's already an incumbent. And once you have an insertion, it's very difficult to pull somebody out of a socket. You know, people get used to things, right? And to drag somebody out, you got to be much better. So we have to be much better, and that's the friction.
Thank you very much for your talk and all your for answer for your all these questions.
Thank you.
Thank you, Professor Amish. Thank you, Dr. Abdullah. It is time for our first technical discussion for the day. Automotive and Aerospace Electronics, Professor of Electrical Engineering at McGill University. Please welcome Professor Murad Al-Jamal.
Assalamu alaikum jami'an. Good morning, everyone. Very happy to be here since the last time, which was a few years ago. I was introduced as a professor at McGill University, but actually I've been more involved in industry for the last 10 years with a company called MEMS Vision. I'm going to talk about it a little bit today. So MEMS Vision was a spin-off from McGill 10 years ago, and it was to commercialize the technology, the MEMS technology that was developed at the university over several years before that. The company is headquartered in Montreal, Canada, and we have a IT design center in Cairo, Egypt. So I travel a lot between Montreal and Cairo because of this. The technology that was developed and is being commercialized is mainly a MEMS technology. And what's new about it and what's unique about it is that we developed a method to build MEMS devices based on silicon carbide. Now, this is different from the silicon carbide that I've been talking about this morning, but the material is the same, and it has a lot of advantages as mechanical advantages as a MEMS device. The main challenge or the main inventions that were there was it was not possible before to sputter or deposit silicon carbide, and silicon carbide being a very strong material, it's also very difficult to etch, to process in a regular fab. So what was developed is a technology that allows using CMOS equipment to standard equipment to build silicon carbide-based MEMS devices. Now, about 10 years ago, I was associate VP of research at McGill. So I was responsible for the commercialization of all the technologies, R&D technologies from McGill and getting it out to the market. And that allowed me to come here with a big delegation from the university to visit several universities and research centers in Saudi Arabia. And at the time I met His Highness Dr. Turki bin Saud. And I told him that we're doing silicon carbide, and you know his background is aerospace, and he's a graduate from Stanford, but he got very, very interested in silicon carbide. And the reason for this is that the silicon carbide, because it has very good mechanical properties, is very good in aerospace application. And he thought, okay, if you're doing silicon carbide for MEMS, then go ahead. That would be a very good topic to work on. And we started a collaboration between McGill, the company MEMS Vision, and CAXT. Now, this is how the relationship started. And I would like to take this opportunity actually to thank everyone here at CAXT for the invitation, especially my former student, Dr. Ahmed Al-Fifi, who worked on MEMS and did very, very good work. One of the best, actually, research work on MEMS that was done in my lab. and we continue to collaborate with him. So let's get started with this presentation. So I'll be talking about sensors for automotive. I'll be focusing on sensors, mainly semiconductor sensors, because there are many type of sensors in cars. So what's happening, as we all know, that there was a shortage in chips, and I'm going to talk about the reason for this, especially for the automotive market. But the automotive industry is actually, as you probably know, seeing a very big change over the recent years. First, there's a big increase in semiconductor content, and this is good news for us. Us working in semiconductor, that's a very big market, and there are a lot of opportunities for innovation and for business as well. Of course, electrification is another driver for this big change. There's also the supply chain issue, which I'm going to talk about. Why it has been so critical for the automotive industry. And then there are several newcomers in the industry, Huawei, Tesla, and Lucid. And I think that Lucid actually is starting a fab here, right? Or setting up a fab in Saudi Arabia. So it's a good time to be. And then, of course, China is intensifying their game and their involvement in this. But I'm not going to discuss this in this talk. So why was there a big shortage, especially in the automotive industry? If you look here at the TSMC and the revenues in 2020, you'd find that about half of their revenues were from a smartphone, and then the other half was IoT and other applications, and only 3% from automotive. So when the pandemic hit and when there was a big demand on semiconductors, big fabs like TSMC favored the smartphone applications. And this is why, if you look at the right, the number of cars sold is 76 million units of ICs in cars, whereas you have 200 million units in laptops, 200 million units for TVs, and so on. So the automotive industry was at a disadvantage, and this is what caused this big shift in the supply chain. Now, what is the content? What type of content of semiconductor in general is in the car? It's quite a wide range of chips, starting from the top left, image sensors. There are about 1 to 10 chips in 60% of the cars. The price is $10, which is a good price for chip manufacturers. Microcontrollers, $1 per chip. Well, that's not a very good business, but there are 15 to 80 chips per car. Analog components, 10 to 100. Power discrete. These are also, low ASP type of products. And then comes the AI chips, which one or two per car, and the price is $150. So it's a good business. And then ADAS and all the automatic driving systems, $35 per chip, and there's only one chip per car. So this is the semiconductor field, if you want, for automotive. Now, this is the big trend these days in the automotive industry, and they call it CASE, and this refers to connectivity on the lower left. Autonomous. So connectivity is, there's a lot of connectivity needed in cars, autonomous driving and so on. And then sharing, this is a trend. I'm not sure if it's, you have this trend here in Saudi Arabia, but let's say in Montreal, you can go rent a car. You can take a car from the street, go from one place to the other, and then leave the car there. So sharing cars actually is a big and growing trend. And then, of course, electrification. Now, these are all the applications that come, or the subsystems that come with this type of major trends. I'm not going to go over all of them, but you can see, for example, connectivity. You have safety. You have comfort. You have vehicle to vehicle, vehicle to infrastructure, vehicle to even to surrounding people around. There's ADAS systems and so on. So there's a huge content of semiconductor in automotive. That's the interest in this, in this area. So what I would like to do is maybe lay down the, framework, business framework of the semiconductor in automotive and then sensors in automotive. So what we're showing here is the forecast for semiconductor market in cars. It's expected to grow from 40 billion to 80 billion in 5 years. That's actually huge. So it's originally a very big market. 40 billion is quite big. Now 40 to 80 is also a very big growth. So there is a lot of opportunities and a lot of interest in making this happen. Now, from a technical point of view, if you want, what is the difference between the semiconductor needed for mobile applications and for automotive? Now, in terms of the processes used in mobile application, they go from 28 nanometer to 7 nanometer these days. So these are the latest nodes used. Whereas in automotive, they still go from 180 nanometer to 7 nanometer. So many of the analog chips are still done in 180 nanometer. Frequencies for mobile go up to 2.7 gig. For automotive, they can go to 5.9 gig and even more for radar and so on. For the voltage supply, again, in mobile, up to 1.8 volts. For automotive, you need up to 60 volts. So this causes, requirements for technologies that support this. Temperature, again, 0 to 40, I think it's wider than this, but this is what a mobile phone is expected to, the range that the mobile phone is expected to work with, unless you're in Montreal and it's minus 20 degrees outside. That's another issue, but they designed for this. For automotive, we designed for, from the start, we designed from minus 40 to 115. The operating lifetime is about 1 to 3 years. Of course, they design for more than that, but this is what is expected for the lifetime for the product. For automotive, it's 10 to 15 years. So it's very, very demanding to design anything and make sure that it works well for 10 to 15 years. And then the failure or percentage failure is less than 10% for mobile. For automotive, they will tell you they're going for 0%. So very, very demanding there. Now, as researchers, I think it's interesting to know what are the nodes that are being used for automotive. As I said, it goes from 180 nanometer down to 7 nanometer and less than that. And this has been driven by TSMC pushing and building more fabs for smaller nodes, for mobile applications. But then the automotive market can, or automotive industry can benefit from this. As you can see from the lower left, analog chips are still in the 100 nanometer to 65 nanometer, display drivers, power drivers, and so on. So the entire spectrum actually is of interest for the automotive industry. Now, this shows the world market for all sensors. So when I'm here, I'm mentioning all sensors. So there are sensors, for example, mechanical sensor, pedal sensor, and so on. These are not; they don't use semiconductor. They don't use semiconductor chips. So all the entire market actually is $24 billion. It's a lot of money as well, and expected to grow to 35 billion in 5 years. Now, this is all sensors. Now, for silicon sensors, which is what we're interested in and what this talk is about, it's about 5 billion today and expected to grow to 6.5 billion in 5 years. And this is what we're talking about today, mainly sensors for automotive. Now, I don't expect you to see what's happening there. It's a lot. This is a list of all the sensors that you would find in a car. So it's quite extensive. You can see I have speed sensors and for many applications, temperature sensor, many specs, accelerometers, pressure sensors, and so on. We're not going to talk about these, but because many of these are actually legacy or been there for a long time, I'll try to focus on the emerging ones and the ones which are of interest these days. So, as a high-level picture of the different applications in a car, we have communication applications, vehicle to vehicle, vehicle to infrastructure, and so on. Displays. If you've been in some of the recent cars, it's really impressive the kind of TVs that are in these cars. Lighting as well, in-cabin sensing, and this is what I'll be focusing on. And then there is ADAS, car sharing. There needs some, to be able to share the use of the same car, you need some electronics, some sensors there to make the experience more pleasurable, and then electrification. So I'm going to be focusing on the in-cabin sensing for the remainder of this talk. So what are the sensors which are emerging, and there's a lot of activities working on. The first one is driver monitoring system. So car manufacturers have realized that if they can analyze what's happening with the driver, if he's tired, if he's sleepy, if he's there or not, and so on, this can improve safety and the experience. So there's a lot of, and this requires a lot of signal processing and processors and chips behind that. There's also occupant monitoring systems, so to know how many person is in the car, to adjust the performance of the car, and also to adjust the environment inside the car. Do you need more air circulation? Do you need more filtering of air, and so on? Active noise cancelling, this is also becoming very important as well. And then there is all the environment monitoring, so particle monitoring systems, humidity, temperature, and so on. So some of these actually are shared by other applications. For example, particle monitoring, this is also used in, in building control and in air control in general. So what I'm going to end this talk with is a case study of developing, state-of-the-art sensor for one of these applications, which is a particle sensor. So we've been working on this for several years, actually between McGill and MEMS Vision. The design of a miniature and smart particle matter sensor. It has uses in automotive, and the interest is growing very, very fast. So again, what is particle matter? So it's a complex mixture of extremely small particles and liquid droplets. So it can be made up of nitric and sulfuric acids, organic chemicals, fumes, and so on. And this is generated by all the different types of infrastructure that we have around us. Now, these are classified based on the sizes of these particles. So they're known as PM10, PM2.5, and ultrafine. And each one of them has its own impact on human health. What you see on the right, bottom right, you see this is a picture of the size of a human hair, and then the size of these particles, as you can see, the PM10, the blue one, it's quite small. And the smaller it is, the more dangerous it is, because the smaller it is, the deeper it can go into the lungs and cause health issues. So the 10 PM, the PM10 ones go down to the throat and they can create irritation, but then the ultrafine ones can go down to in the lungs and cause chronic disease. Now, why is it important to measure them and to purify the air if needed? Is that about 7 million deaths are estimated to happen due to this pollution kind of problem. Now, the WHO set some measures to what needs to be done and what are the specs that you need to follow or you need to targets you need to reach in terms of air quality. So they gave for annual mean about 10 microgram per meter cube. And 24 hours, you shouldn't be exposed to more than 25 microgram per meter cube. And you can see there the quality of air in different areas, around the world. Ottawa and Stockholm, they seem to be clean. Taipei is okay, Tehran is getting worse, and then you go all the way down to New Delhi, and then you find that it's it's a disaster there. And I think that the Indian government is aware of this, and they are doing their best to address this. But anyway, WHO gives these guidelines, and the very important thing I want to bring up here is that the guidelines are given as mass per volume. Okay, so the right way of doing it is to measure the mass of these particles per volume and then say whether you are within the limits or not. And I'm going to explain why this is important. Now, the equipment used now for measuring air quality in cities is the one that you see on the right. So it's quite a big equipment, and it's called gravimetric because it measures actually the mass. Now these systems are expensive, large sizes. They don't give you measurements in real time because the way it works is they have filters in there, and there is air circulation, and then they take these filters every now and then. A technician has to come, take it, go to the lab, and measure it, and so on. So it's not a real-time thing. And so companies have been developing solutions, and what you see on the right, this is the most common solution, which is that big. It's as big as a packet of cigarette, and basically it has a fan that makes air circulate into a chamber, and inside this chamber you have a laser and a sensor, and what does is that it measures the number of particles in the air, and then from there it gives you an estimate of what is the particle concentration, but it doesn't measure it. That's the thing. It doesn't measure the weight. Okay, all the products out there, they don't measure the weight. They infer from light measurements of the particles and making assumptions. What kind of particles are there? You are in a city, this is probably this. If you are in a desert, probably it's dust. It's sand and so on. And then they give you a number. But it is never as accurate as WHO would like it to be. So we started this. We're looking at this a couple of years ago, and we set this as our objectives. First, we needed to have a mechanism to segregate the different sizes of the particles, and then a mechanism to sense it basically by weighing it, and then a mechanism to reset the sensor after each measurement. Now, this business of resetting sensors is a very, very big business. It's very, very important. I always tell my students and engineers working for me, and it's one thing that I don't see much in academia, and it kind of irks me because a lot of research is done, and then the researcher says, okay, I have the highest accurate sensor doing this or that, and then you find out that the sensor cannot be reset. Well, the sensor needs to be reset all the time. If you cannot reset it, then there's a problem. And we found this to be an issue with humidity sensors. Now, there is so many humidity sensors out there that you would think that, okay, it's a piece of cake. Actually, it is not, and one of the biggest challenges in humidity sensors is to reset them. So if if humidity becomes 100%, like say in Dubai, and then it drops, most sensors that are being developed, they will not drop fast because it's like a sponge and it gets soaked by humidity and it doesn't repel, so the sensor doesn't reset. So resetting a sensor is very, very important. And 90% of research done in academia doesn't address this. So anyway, so when we started this, I kept telling the engineers working on this, if you can't reset it, forget about it, we're not going to do it. So here we said the first thing is we need to segregate the particles depending on the size, and the way we thought of doing it is by using microchannels and designing these channels so that there is air, absorbed into these channels, and then the aerodynamics and the inertia with which these particles are moving will decide where they would go, in which chamber they would go. So the big ones will go to the right, for example, and the small one, or actually the other way around, the big ones will continue with the inertia, and the small one will get absorbed in the other chamber to be measured. So this took a lot of analysis and simulations to get it right. And then after this, we thought, okay, so how are we going to measure it? So we built what we call a micro cantilever or micro platform that vibrates, and the frequency of this platform will change depending on the weight that is sitting on it. And then this was actually built in a standard MEMS fab that had piezoelectric capabilities, and this is an SEM of one of the devices that we built. Okay, so it's to measure actually to measure the particle weight and not the numbers. And then, and this is actually, I'm very happy with this one, I'm very proud of it, is you would think, for example, if you take this, your system and put it in a place where there is particles, it will measure. But that's not true, because nothing will bring the air into your device. So we need to add a fan. So we add a fan, and then we thought that, okay, by adding the fan, the particles will go in and will sit on your measuring device. But they won't sit. Actually, they will just pass, and you will not measure anything. So we found that we need to find a way to make the particles get attracted to this weighing device. So we used a temperature gradient, and this makes the device, the particles go and sit on the weighing platform to weight it. And then after this, you need to get rid of it, and this comes the resetting part. And this would be done by switching, making the hot plate on the bottom side and the cold plate on the bottom, and then the particle would release. So there are actually many patents that got into, getting the entire system put together. And this is the, this is how the system looks like. So you have actually a lot of electronics put on the PCB, and then you need to integrate this PCB within this 3D structure. And then you have to find a way to connect everything to it, connect power to it, and so on, put the sensor there. And then at the bottom there, the black box, this is a fan. So you need to find a very, very small fan so that the size remains small. So to build this kind of system, as Dr. Hisham Haddara said yesterday, actually sensors are full systems, okay? And you need to think about them this way, not think about them as a semiconductor chip or an IC. Chips are known to be, you can design a chip from scratch in 8 months, and we work with partners and customers, and when we tell them it's 2 years, 3 years, they don't believe us, but it's a full system. You need to do this. You need to do electrical work, MEMS design, fluid dynamics analysis, mechanical design, and so on. So this is the actually the third or maybe fourth prototype that we built. As you can see, the one on the left, this is an optical from a main competitor, which is a Sensirion. It's a Swiss company. And the one on the right is the sensor that we are proposing here. As you can see, it's a quarter the size, and we are actually pushing to get smaller. The bottleneck is the size of the fan. And there's a lot of innovation there, and we have ideas to make this. We want to make it as small and as thin as it can be, so that we can put it in mobile phones, and then everyone has a way to measure the quality of the air in their mobile phone. This is an example of test setup. How do we test these devices? So on the right, you see we have incense sticks, which you burn it, and as you burn it, it creates particles in the air. And then we found that these particles are generated with water vapor, so you need to remove the water vapor. So this is why you have this tube that has some gel in it to absorb water. So when it goes into the other tank over there, you will just get dry particles. Now this is it's interesting to look at this and say, okay, that's fine for one type of experiment, but now how do you do this to build millions of these sensors and to calibrate them? It's quite a challenge. Okay, how do you calibrate this thing, knowing that this is what you need to do? You need to create a very well-known amount of particles in the air and then calibrate it. So it's quite a challenge. These are experimental results showing that actually the idea works. So you can see we start at 0. There's no particle in the air, and then smoke is introduced, so you see the measurements increases, and then the green line, you get a release from the chamber, so it goes down and up again and then down. So it's actually working as expected. And I'm quite happy. These are very, very recent results, not shown anywhere else. Now, sensor calibration, actually, not testing. Sensor calibration and testing is much more involved and much more demanding, especially when you're doing it in industry. So in ICs, the package is usually a standard package. You know, it's square or a kind of square chip, and we know how to test it. Testing is often done on chip. So you have these big testers, like the one you see on the bottom. You have this big tester, and then you have these probes that go down, test every chip, and then you're done. But for a sensor, actually, this needs to be it's not standard. The packages are not standard, and for every sensor, we found that you need to develop the entire infrastructure to test and calibrate. Now, temperature testing usually for chips is done at one point. You measure it, it's working, then you get the next one. For sensors, you cannot do this because most sensors are very sensitive to temperature, and you need to calibrate over a very wide range of temperatures. The physical stimulus also, the sensor needs a physical stimulus, not only electrical one. So if it's a temperature sensor, you need to create temperature. If it's a humidity sensor, you need to create humidity. And then you need to create this for a big number of sensors, and then you need to measure it and calibrate it. So we've been talking actually to big manufacturers of test and calibration equipment to see how they can help us with the particle sensor. None of them has any solution. So we are deciding to do it ourselves, and I tell my engineers we are, our background is IC design and MEMS design, and what are we doing? And they tell me we are turning into a test and calibration company because we need to do this, and no one can do it for us out there. I'm showing up there some of the, we don't do these earpods. Is just to show you the size. As you can see, different type of sensors. The particle sensor. The one in the middle is this is a pressure sensor. As you can see, it's very small, 7 millimeter by 7 millimeter. It's one of the smallest, actually. It will be one of the smallest on the market. And you can imagine that you need to calibrate thousands, maybe millions of these. And to calibrate them, you need to connect them to tubes and measure how what their performance is, and then generate the calibration coefficients. How do you do this in mass production? It's a very, very big, actually, challenge to do this. The very small one on the bottom there is a humidity sensor. This one is about 2 millimeter by 2 millimeter in size. Now, how do you calibrate this one? If you see on the bottom left, this is a chamber that generates humidity and temperature, and we put in there 20,000 chips at the same time. Now, we need a very high accuracy to do this, and how do you guarantee that every one of these sensors, which is 20,000 sensors, how do you guarantee that each one of them has the right temperature? If you want to calibrate for 0.2 degrees C, how do you do this? If you want to calibrate for 1% accuracy, how do you do this? How do you ensure this inside the chamber? Very, very difficult. And it's been, the story of our, work for the last several years. So to conclude my talk, this is actually the forecast for in-cabin sensors. Today, it's at $500 million market, and it's going to grow very fast to 3.5 billion, and the big contenders there are the particle sensors, gas sensors, as well as the occupancy and driver monitoring sensors. Thank you very much for your attention.
Thank you, Professor Murad. Assistant Professor, Electrical and Computer Engineering, please welcome Dr. Yating Wan.
Thank thanks for the introduction, and thanks for Kai and Xiaohang and Thomas in organizing this wonderful event. So this is Yating Wan from UC Santa Barbara, and I'm going to join KAUST in EC department as assistant professor in 2 months. So it's my great pleasure here today to present to you the quantum dot laser and its integration with silicon photonics integrated circuits. So silicon photonics has found very wide applications from datacom, telecom to LiDAR, chemical sensing, and optical metrology. So as the most promising integration platform, silicon provides a variety of passive components from modulators, low-loss waveguides, detectors, MEMS, etc. But silicon is an indirect bandgap material, so it has very low internal quantum efficiency, and that makes silicon a very bad candidate to make lasers. So actually, the best group 4 laser has a special current density as high as 300 kiloamp per centimeter square, and which is around 3,000 times higher than the typical 3.5 lasers. So to integrate onto lasers, onto the silicon photonics, you really need to integrate 3.5 materials together. So to integrate 3.5 lasers onto the silicon substrate, heterogeneous integration is a very promising approach. So it was invented in UCSB around 10 years ago, and now it's commercially available in many companies, and Intel is shipping millions of transistors each year using this technology. So it can not only integrate 3.5 lasers, it can flexibly add different, very different material functionalities onto the same photonics chip. But of course, every coin has its 2 sides, so you still need to do this pretty complicated bonding, and you still need a 3.5 substrate, and you can see from the table it's much more costly and constraint the scalability. So alternatively, monolithic integration is considered to be more economically favorable and also provides the best natural heat sinking. But you still have to deal with the fundamental material difference between the 3.5 and the silicon, and that gives to a lot of crystalline defects during the growth that can seriously degrade the device performance and limits the lifetime. So actually, people are starting to investigating growing quantum well devices on silicon like 30, 40 years ago, and the device performance is still far behind the native substrate, and the lifetime is limited to around just 200 hours. So to achieve native substrate performance, you really need to use quantum dots instead of quantum wells at actual region. So by virtue of the 3-dimensional confinement of carriers, quantum dots really promise a lot of advantages over its quantum well counterparts, including the lower special current, much higher temperature tolerance, near zero line with enhancement factor, so that you can make photon integrated circuits without the big and expensive isolators, and ultra-fast gain dynamics that is important for molar lasers, and reduce the carrier diffusion length that really makes it possible to make ultra-small devices. But most importantly, the strong stream field induced by quantum dots can suppress the in-plane movement of dislocations. So this much improved defect tolerance gives rise to much better device lifetime, which is around over 100 years in room temperature and over 10 years in 60 degrees C. And recently, we just get breakthrough results of record long lifetime at 80 degrees C. And so if people are interested, can refer to the previous speaker yesterday, Chen Shang, also from UC Santa Barbara, and about our robust high temperature operation of quantum dot lasers growing silicon at 80 degrees C. So we have this very long device lifetime, and we are guaranteed to investigate more in the device. So there are a lot of recent progress in quantum dot devices on silicon, including this ultra-low photocooling crystal lasers and some million special micro-ring lasers, and this couple cavity tunable laser that doesn't require EBL or regrowth, and this 20 gigahertz molar laser that has over 1 terabit transmission capacity, and very low dark current photodetectors that basically using the same materials and the same device fabrication as the lasers, and high gain, high saturation semiconductor amplifiers. But in addition to this much improved material quality and individual device performance, you really need to consider how to really do this full integration. So basically, for photonic integration circuit, there are two approaches. One is indium phosphide-based monolithic integration, and the other is silicon photonics. And to build quantum dot-based integrated photonic integrated circuits, you can leverage both these technologies. So following the first direction, you basically form all the photonic functionalities in the 3-5 and just use the silicon wafer as a pure handling substrate. And in this case, you can still leverage the lower substrate cost, the larger wafer size, the lower thermal impedance, and also the very advanced CMOS fabrication. So there's a lot of technologies available in indium phosphide based integration, and you have to transition that to gallium arsenide material integration. And following this direction, we demonstrate ray-gone quantum dot DV lasers on silicon by achieving a very high-quality MB ray growth capability in these gallium arsenide-based materials, so that we are able to combine different band gaps into one optical chip. So comparing our results to the state-of-art like device qualities in other groups, so it's much better in terms of spread current, semi-temperature ratio, maximum power, temperature, and also much smaller line widths. So actually, the solitary quantum well lasers, you have like megahertz line widths, but we are able to decrease it to just 40 kilohertz just by changing the quantum wells to quantum dots. And more importantly, the quantum dot has a very small line width enhancement factor, and that enables us to do this system demonstration without using a very bulky, expensive optical isolators. And we are able to get an aggregate transmission capacity over 640 gigabit per second using these 5 channels from the laser wavelengths and a 64 gig bond PAM4 modulation. So it's very important to note that these quantum dots can be very versatile by changing the growth condition. So you can easily increase the gain bandwidth. And actually, we can recently experimentally extend it to over 127 nanometer, so that you can actually extend the laser wavelengths well beyond the current test range. And actually, you see this schematic we polishing a laser photonics review at the journal cover, that we can easily scale to 1 terabit per second using this technology. And it has also won the TLIN Innovation Prize last year, which is one of over 2,000 technician submissions. And the second direction is probably more interesting, because we are now coupling the laser light from the quantum dot to the silicon waveguide, so that we are really in the realm of silicon photonics. In this case, you have to combine the benefits of and also the challenges of direct growth and heterogeneous integration together. So the main challenge here is to change from indium phosphide-based quantum well EPIs to the gallium arsenide-based quantum dot EPIs. So there's a lot of optimizations you need to do in terms of the material selection and device fabrication and device design. So this is our first version of device, so that you see the light was covered both the 3-5 region and the silicon waveguide, and you use the taper to transition the light from the quantum dots region to the silicon waveguide. So this is over around 16 lithography steps. So basically, you create the surface grading by EBL and also the vertical channels that can facilitate bonding and pattern these silicon waveguides, and this bond is quantum dot EPIs onto the SOI substrate and remove the substrate, and then do this PMS paddling so that the light can be coupled from the quantum dots to the silicon waveguide, plus a separate transition from the N gas and a metallization from P and N, and dedicated passivation and VO pulling for the probe deposition. So this table summarizes our results compared to the published results from other groups. So it's very important to notice that there is a synergistic relationship between the unique properties of quantum dots and the silicon. So by integrating the quantum dot lasers onto the silicon substrate, you not only leverage from the benefits of using silicon as a substrate for lower cost, better scalability, but actually it performs even better than the native quantum dot lasers. So, for example, the line waves. So actually, the quantum dot heterogeneous integrate lasers can perform much better than its like this native on its native substrate. So you see, recently there's a lot of progress in narrow line width lasers. So, but this improvement can be categorized into two categories. The first direction is changing from quantum wells to quantum dots by virtue of this low line width enhancement factor. And then the other one is to use this on-chip external cavities, either by gratings or ring cavities. But the most important thing is that if you combine this low line width enhancement factor of quantum dots with this high Q quality, high Q cavities with low silicon or silicon nitride waveguide loss, you can really make substantial improvements in line width. And that is very important for a lot of applications, for example, DSP, free coherent lines for datacom and telecom. So what is missing? So actually now we have got pretty good performance in terms of energy efficiency, copper power, and the lifetimes are also entering the realm of commercial relevance. But most research still focus on lasers. You really need to integrate other ingredients for photon integration, like you have to demonstrate the performance photodetectors, modulators, amplifiers using this material, and you need to like couple the light from quantum dots to the rest of the components. So to achieve this active-passive coupling and co-integration, we'll continue in these two directions we previously described, and especially we'll focus on the heterogeneous laser integration on silicon. So now we have established a collaboration with Intel, and we are using Intel's 300mm silicon photonics platform to pattern the silicon waveguide, and then they ship back to us, and we do all this bonding and subsequent processing. And so, you know, the heterogeneous integration has been very successful. They launch a lot of startups, and Intel is using this technology to ship millions of transmitters each year. And substantial opportunities can be built upon what has been achieved through this quantum well heterogeneous integration by changing the quantum well epi to the quantum dot on silicon epi to both improve performance and reduce cost. So currently, datacom is still the biggest driver to pursue silicon photonics, but there are more advantages and opportunities beyond the data centers. For example, the very dense integration is very important for optical phase array-based LiDAR, right? And for space applications, radiation damage is really a concern, and the very high tolerance to defects of quantum dots can find its applications here. And also AI photonics or neuromorphic photonics. So currently, they still use fiber packaging to bring light to the chip. But in the future version, especially spiking neurophotonics, you really need the on-chip lasers. So basically, you have to combine all the optical signals in one optical chip, and that really needs these on-chip lasers. And also quantum computing. This is also a very hot topic in silicon photonics, and people are starting to find the quantum dots to be a very good candidate to single entangled photon cells. So this kind of research is still at its very fundamental stage. But if the quantum dots can find applications in silicon photonics for the classic applications, so it makes sense to grant them extra consideration in this future quantum computing platforms. So in conclusion, a lot of progress has been made in this last 6 years, and we look forward to seek cooperations worldwide to really transform this technology to seek its more applications and to really transform from journal publications to some things that can really influence the industry. So thank you so much for the attention, and I'll open up for questions.
Thank you, Dr. Wan. He is the Manager of Research and Development at Yokogawa. Please welcome on stage Dr. Mustafa Nasser.
Assalamu alaikum. My name is Mustafa Nasser. I'm an R&D manager in Yokogawa, Saudi Arabia. Actually, we are located in Dhahran, Techno Valley, and today actually would like to give you an overview. Sorry, sorry about this. An overview about a new generation of semiconductor manufacturing system. Actually, here I'm not talking about a new fabrication techniques for semiconductors. I'm talking about something, I can say, a new philosophy of semiconductor manufacturing. As you know, for semiconductor, the clean room is must. You cannot do fabrications without a clean room. But what we are changing here or innovating here is the way of having a clean room. Instead of having a big clean room, suppose that this is a clean room, you need to control the environment here for the whole room in order to do the fabrication of the semiconductor. However, here what we are doing, we are reducing the clean room into a small shuttle that has the silicon wafer and the equipment that fabricate the silicon wafer. And this actually what the minimal fab is doing is reducing the size of the minimal fab to that small unit and shuttle. Okay. First of all, let me just give you a quick overview about Yokogawa. Actually, Yokogawa is a Japanese company founded 100 years ago as an electrical lab. Our main system and technology is control system and instrumentation, and as well process solutions. And we have as well other business in aviation and also in pharma. And one of the new solutions that we are actually handling now, it is the minimal fab. Actually, minimal fab, it is not manufactured by Yokogawa. Yokogawa is a system integrator. This system actually is developed by about 40 Japanese companies. It's a consortium of companies. And Yokogawa is the system integrator of that system. As I mentioned, Yokogawa is an international company. Our head office in Tokyo, and our regional headquarters in Bahrain, and in Saudi in Dhahran, Techno Valley. And we have other offices here around Saudi Arabia. Okay, now coming back to the minimal fab. Minimal fab actually is a novel system, as I mentioned, as a new generation of semiconductor manufacturing, which be suitable for education, R&D, prototyping, and even actually low volume production. It has a lower cost investment compared to the mega fab or standard fab. It has a faster processing, and as well, it requires small wafer size, and you can have a flexible production schedule, and as well, you can compare the size actually of the minimal fab compared to the mega fab. You can see the huge difference. You can set up this minimal fab tools within a room with 20 meters square size, compared to the mega fab, which requires a huge area. So here actually we are looking at the minimal fab as an ideal system to seed actually the semiconductor in Saudi Arabia. For education, it can be used to develop the local semiconductor talent, for training the student in IC fabrication, and as well it can be used for R&D to foster the research and development for micro devices and sensors, and as well for prototyping, to accelerate the prototyping, and ultimately actually it can be used for a low cost. It can be used as a low cost manufacturing system for low volume production and startup as well. So actually, minimal fab actually it is not a replacement or a competing system with a standard fab. Actually, the mega fab usually it is intended for mass production in order to be an economical system. However, the minimal fab is focusing on high mix and it's cover a wide range of product and customized circuit, such as these devices and the business domain. And that's actually the difference actually between the minimal fab and mega fab. They are not competing, but you can see it as a complementing or finding an alternative solution for such domains. Instead of going to do some customized circuit in mega fab, which is costly, you can utilize the minimal fab to do such IC fabrication. So now let me just give a small comparison between the standard fab as well and the minimal fab. Actually, you can look to the capital investment for the mega fab. As you know, most of you, that is a huge investment for the mega fab. While the minimal fab, it has much lower actually investment than the mega fab. The lead time, of course, would be shorter because you have all the tools there. The wafer size, the standard wafer size used in mega fab is about 12-inch, while in minimal fab you can use only 0.5-inch wafer. Of course, as I mentioned, the intention here for minimal fab is not mass production. So while in the mega fab, the mass production is the main purpose. That's why you can see the number of chips per month, it's lower. I will just go now quickly through some advantages of the minimal fab. The main advantage actually for the minimal fab, you know, that when you develop a new device or IIC, it's go through different stages. First, you need to develop it in the R&D labs. Then you need to do the prototyping maybe in another facility. And finally, you have to send it to the fab to do the final product. Actually, this one is creating a death valley between these stages, which actually delay the process of IC fabrication. Here, actually, while if you're using the minimal fab, we are actually eliminating such death valley between these stages, which actually accelerate the device development and production. Another advantage, so actually you can see the key advantage of the minimal fab is the clean room-less environment. Actually here, we are not eliminating the clean room, but actually we are reducing the size of the clean room into just a small shuttle in which you place the wafer and the unit that do the process. And in order to ensure that there is no contamination with when you move the wafer from one unit to a unit, and when you open this shuttle to do the processing, you have a wafer transfer system, as you can see below, in order to make sure that there is no contamination happen when you are moving the wafer and opening the shuttle inside the unit. As I mentioned here, we are using only a 0.5-inch wafer, and one of the advantages that since we are using these tools, we can produce as much as we required, not as the mega fab. We are looking to have a high demand in order to be economically operate a mega fab. Here you can produce only one chip or few chips, which actually is very suitable for some customized circuit and for some domains, and for R&D and prototyping in research institutes. Of course, the power consumption, it will be much, much less than, I can say, the mega fab. Another advantage is that we are is a faster processing because we are using maskless exposure using the direct drawing method, which actually considerably reduce the time compared to the conventional processes. For example, this SOI CMOS circuit, which actually it required 98 processes, is done only in 5 days using this minimal fab tools. So now, what minimal fab can do? Actually, minimal fab, it cannot do everything. It cannot fully replace the mega fab. The main things that can be done actually by the minimal fab is Internet of Things and can say MEMS. Actually, the minimum resolution that can achieved by the minimal fab is 0.5 micron. It doesn't reach actually with the current technology to the nanoscale. But with the micro scale, we can cover a wide range of devices that doesn't require actually the nanoscale. such as the Internet of Things and MEMS. Here you can see here, actually, if you look into here, this figure, you can see the history when we start the minimal fab development by these 40 companies in Japan. And some of the devices, they are fully fabricated by minimal fab. And during the development, you can see we are increasing the number of tools that can do more fabrication processes. Still, there are some tools under development, but it can be compensated by hybrid processes that can combine both minimal fab and the classical mega fab tools. Here is one example about MEMS pressure sensor that's fabricated by the minimal fab. You can see the complete wafer processes done in only 4 days. This another examples for MEMS that's fabricated by the minimal fab. Here are also another examples of some devices that's also fabricated by the minimal fab. And this actually one case study. We designed a circuit with this, for the JAXA, which is actually the Japan or Aerospace Exploration Agency. This is actually a 4-bit ALU with a shift resistor and the I/O having 1,000 transistors. This is already fabricated, and the performance was accepted by JAXA, and we are now trying to develop it more to satisfy their demands. And as well, we try in Japan. They have some contact with the Japanese university to implement this minimal fab. We request actually we receive a request from other university and other entities as well from China and other countries to deploy and implement minimal fab. So here actually, this is just a brief about the minimal fab specification and advantages. And actually, we are trying now to deploy this system here in Saudi Arabia and have it as one of, I can say, the first semiconductor manufacturing utilities here in Saudi Arabia. Thank you very much for your attention, and I'm happy if you have any questions.
Thank you, Dr. Mustafa. The University Program Manager, let's all please welcome Antonian Klotz.
Okay, good morning. Assalamu alaikum. So I hope I can use this one. Okay, so we are already at the first slide. So what is Cadence? So what is the mission of Cadence Design Systems? So the mission is that we are an intelligent system company, and our mission is to innovate technologies essential to building great products that transform lives. And for this, we are providing different tools. It's software, it's hardware, it's IP, and so the designers worldwide using our tools to create these great products. So this was still a... okay. Good. So what is the strategy of the company? So we started from this orange circle, so EDA. So basically, 35 years ago, we started providing tools to develop ICs, to develop PCBs and packages. And from there, we expanded on higher level. So now we are also providing tools for system design. So this is for the design of the system, but also analysis of the systems, which includes also multi-physics analysis. And where we want to go is AI, machine learning, data analysis, and later in my presentation, so I will show you what we have already achieved in this area. And so just as an example, so often vertical, so automotive, autonomous driving. So you are using our tools to develop the IC, so which is performing some operations, for example, machine learning. So then there's also a package that you can design using our tools, then the PCB. And then once the PCB is installed in the car, so then we also provide machine learning algorithms, so which are used for the autonomous driving. So, but this is an example of just one vertical, but we are serving different verticals, also aero defense, medical, hyperscalers, so you name it. Yeah, so these are our products. So we are so the products are divided in 5 business units. So the first one is the intellectual property. So here we are providing IPs, for example, Tensilica processor IP, which can be integrated in a system on a chip. So then we have digital and sign-off. So this is for the digital back-end and sign-off tools. Then the system verification, so this is basically the digital front end. So here we have software, but also hardware. So the hardware emulators, so which are speeding up your verification of your design. Then custom IC, packaging and PCB. So here we have our leading product, which is called Virtuoso for the analog design. And also, I will show you later how the PCB design, PCB analysis is now getting more intertwined with analog design. And as our latest addition is this multi-physics system analysis. So here, this is electromagnetic, thermal, and even CFD analysis, what we can offer designers to verify the system. Okay, so now let's pass the commercial. So now let's go more into the technical details. So, the industry is always still following the path of the Moore's law, and so now the question is, so why we are doing this, and why now we are going from 7 nanometers to 3 nanometers to 5 nanometers, and so these numbers are from TSMC. So if you now switch from 7 nanometer to 5 nanometers, so then you have a performance gain of 30% using the same power. Or if you want to save some energy, so then you keep the performance level, but you save 30% on dynamic power at 5 nanometer. At 3 nanometer, so this is another reduction of 10 to 15% compared to 5 nanometer on performance, or 25 to 30% on energy savings. Also, there's still a big density increase. So from 7 to 5 nanometer, you have 1.8 factor of gate density increase, and then another 1.7 for 3 nanometer. But this all doesn't come for free. So so some cost is associated here. And as you can see on the upper left graph, so now it's not longer the case that the cost is decreasing when you are, so cost per transistor is decreasing, so when you are switching to the newer technology node. So actually it remains pretty stable. So that means that in the future, so in the past, so when you had let's say a processor in 65 nanometer, and then you wanted to add yet another core to the processor, so then you just go down to 45 nanometer, and then the cost of the processor stays the same, but you have double the performance because of the second core. So this is no longer the case. So now if you want to add more cores, so then the price is increasing of the chip. And why this is the case? Mostly because the lithography is getting more and more expensive. So now for the latest nodes, we are switching to extreme ultraviolet lithography, so which is very, very costly. Another problem is that while you still can shrink the digital part of your chip, so the SRAM and analog parts, they cannot, so they are not shrinking well. So therefore, the size of your chip remains the same, and now it's dominated by SRAM and by analog. Also, there are big problems with parasitic capacitance and parasitic resistance. So there are a lot of elements which need to be extracted, need to be simulated, need to be taken into account to ensure that your system is still working properly. And also there's a huge local variation in the layout. So you can imagine, so now during the lithography process, so now if we start really counting photons which are falling on the wafer. So then if there are few photons there and there, so different, so then you have already a variation in the layout with these fine structures. And all this comes at a cost. So it's getting more and more costly to develop SoC in the advanced technologies. But still, it's very interesting is the graph which is on the bottom. So this is the high volume start for a certain technology, and you can see that so even if the technology becomes more complex, so still it's possible to increase the number of wafers at the high volume start. And this is very remarkable even for historic analysis, because usually if you have a very advanced technology, so only few people had access to it. So maybe it was used for military or for very costly devices. But now you see that the very advanced technology, so 5 nanometers, so it's immediately available to basically all of us. So it's in our latest smartphone, and we don't even think about it, so that how complex it is to create such a technology, so to enable a high volume output of it, and then put it and then provide it to population. So this is a very interesting observation. And also interesting observation is that still, so there were some predictions that the costlier the process becomes, so the less designs will be started, so the less chips will be produced. But this is proven wrong. So you see that the demand for the latest nodes is still ongoing, and it will be the case in the future as well. So here we have a slide from ASML. So basically, so what needs to be done in order to keep the Moore's law going? The clock frequency is not really increasing. So in the last 10 years, also the transistor density is so litho and transistor densities is there are modest increases. That transistor energy efficient performance also is stalling at some point. So the only thing what can still be increased is the system energy efficient performance. And the question is now, so how to optimize the system so that this can still be achieved. And the idea is now going back from SoC to advanced packaging. So basically, the pendulum is now swinging back. So first you wanted to integrate everything on one single chip. So now you are starting to decombine the SoC into so-called chiplets. And so why do you want to do this? So one reason is that the bigger the SoC becomes, so then the lower is the yield. So if you now decombine the SoC into smaller parts and then combine them together with a chiplet approach, so then you can increase the yield of your chip. The second reason is, as you have seen, the SRAM and the analog parts are not scaling well. So therefore, now if you just disaggregate and put the SRAM and the analog parts on a different chiplet, so still you can continue shrinking your digital, but then you can just put the chiplets of SRAM and of analog combine it with your digital chiplet. And also you can combine different technologies, so it must not be that you have chiplets in just one single technology, so you can have different technologies as well. Also, another reason is that if you want to have a very short and speedy interconnect. So then you can use the third dimension in order to bring your memories closer to your core, which does the computations. So if we now look at the different generations of packaging, so you see that the difference is always so how many interconnects you can have per area, and what is the spacing between the bumps. And so now, so we started with the system in package, and then went to 3D SiC, 3D SoC. So this is where we are now. So where we are combining wafers together, and also do a wafer-to-wafer sequential processing. And so what will be in the future is the 3D IC, so where we stack single transistors together so that you have NMOS and PMOS transistor stacked vertically. And so you see the interconnect density is always increasing. So here we have a chip, so which it does not exist yet, but very advanced research institutes like IMEC, so they are already proposing this architecture. So now if we look at this, so the laser is unfortunately not working, but so we have basically two wafers, so which are bonded face to face. So you see on the top there's the substrate of the first wafer, and then there's the substrate of the second wafer, and the metals are basically bonded together. And then you also have you have BPRs. So BPRs are the buried power rails. So that means that your power connection to the standard cells is no longer in metal 2 or metal 3, but it's in the substrate. And then so the power comes from the substrate, from the buried power rails, and then gets distributed through the standard cells. And also there is a possibility to do the power routing on the backside of the substrate. So then you can imagine, so now if you have a signal, so which the signal needs to go from the substrate of the top wafer, also from the standard cell of the top wafer through the bump, so just to get out of the chip. So now the signal needs to go first through the metals of the first wafer, then through the bonding plates, through the metals of the second wafer, then through the TSV, and then goes to the bump. So you can imagine, so in order to enable the functionality of this chip, so you need to do a lot of checking. So you need to check for timing. You need to check for signal integrity. You need to check for power. You need to check for thermal, and all of this requires handling a huge amount of data. So basically, Cadence has introduced Integrity 3D IC platform. So where you have one platform database, and in this database you have information about all the 3D information of your design. And now with this database, so you can do all kinds of checking. So you can do thermal check, power check, timing, DHC, LVS. So then you can go into the packaging design. You can go into analog design, into PCB design, and then make sure that everything is combined and working together properly. So now I have only very little time. So here, yesterday there was a presentation about RF, so where it was mentioning that the RF flows and analog flows are coming together. So here I have an example of such a design flow. So here the idea is that once you design an analog block, and then you still want to make sure that when you integrate this block in a package and into a PCB, that it's still working properly, so that the parasitics from the packaging from the PCB are not influencing the performance of the analog design. So here in this case, it is possible now to annotate the parasitics into so parasitics which are coming from the package and from the board into the analog simulation. So you can simulate your analog design and take into account the parasitics from package from PCB, so that you have the full picture of all the parasitic influences from PCB and package. And so there are a range of cadence tools which are integrated together, so which are pathing the design data, the simulation data, the parasitics data to each other, and therefore a complete picture is available. So I have still 1 minute? No. Okay, so then just quickly about the machine learning in EDA tools. So let me just show you that we have several tools, so which are already benefiting from machine learning. The blue ones are the ones which are where machine learning algorithms are integrated in the tool itself, so it's transparent for the user. So you get better results, but you don't have the visibility, so why the results are better. While the green ones, so here it's the machine learning is used to optimize the design flow of your design. So basically, the machine learning is controlling your tools, and therefore it basically creates more frees the capacity of a designer, so he can work on more designs or more blocks in parallel. So here it's about how it works. So for a digital flow, so basically your genus in novus tempus voltus tool, so the synthesis, the implementation, and the checks are integrated into one environment, and your machine learning tool is basically controlling this and provides new inputs and optimizes the design flow. So this is basically what I wanted to tell you about cadence, and thank you very much for your attention.
Okay, thank you everyone for being here today, and thanks for attending this session, the Automotive and Aerospace Electronics. And thanks for the speakers for presenting today and sharing their time and their knowledge. I would like to welcome Dr. Professor Murad. I have worked with him before, and he's the one who gave me the inspiration to continue my work in MEMS. Thank you for being here today. We are glad to have you and have all the speakers. Dr. Wan, Dr. Yusuf, and I'm sorry, Dr. Mustafa, and Dr. Anton. Okay, let's start this panel discussion with a question from the audience. Go ahead, Dr. Mohan. Mic, please.
Well, my question is to Professor Murad Al-Jamal. Well, when he placed like a picture of sensors, and particularly pressure sensors, I'm curious to get some information about those pressure sensors. What is the key, like for example, what is the key material in that sensor? And like for example, you know that like in terms of pressure, the range of pressure, how many gigapascal? Like for example, you know, silicon transform at 10 gigapascal, germanium at like 8 gigapascal, and can be used to detect pressure. Gallium arsenide at around 15 gigapascal, and all these values, we can play with it with the temperature. Like for example, we can increase this pressure value with the cooling down the material or heating up. So could you please elaborate on that? Thank you.
Okay, thank you for the question. Actually, there are two types of pressure sensors we're working on, and they're not for high pressures. They're mainly for IoT applications, so for atmospheric pressure. So they're very sensitive in the sense that they have a sensitivity of centimeters. So as you move the sensor up and down, it can measure, the height at which you are. So it's mainly for atmospheric range. And if you need higher pressures, we use our silicon carbide technology so that we can strengthen the membrane so that it can maybe go up to 10 atmosphere in pressure. But we don't do very high pressure applications, which are actually other sensors used in the automotive industry target this, but this is not what we are working on.
Thank you for all the amazing talk. I have one quick question for Dr. Yating. It's a question about the concept. So I'm wondering that how do you understand the concept of the heterogeneous integration and the monolithic integration, especially in terms of the material epitaxy and some device integration? Thank you.
Thank you for your question. I think heterogeneous integration is very, very close to commercialization. Actually, as I mentioned, there are already a lot of startups, and Intel is shipping a lot of transceivers based on this technology. And the monolithic integration is still currently at the research level. So as I mentioned, all the progress still focus on the material level and individual device level. But very, very little efforts are devoted to the full integration, especially apply this technology to different applications. So I think monolithic integration is more favorable in terms of economy scale, and also it provides better heat sinking, but it's still a long way to go for commercialization.
Thanks for the speakers for these great presentations. I have two questions for Dr. Murad and for Dr. Mustafa. So, Dr. Murad, the air quality sensor that you worked on, from what we saw, it separates large particles and small particles, and there are multiple grades of small particles. Have you looked into these sizes? Into getting more chambers, for example, in this design to separate even smaller particles. And as you said, that the smaller the particle, the greater the danger. But however, if we grouped all of them together, is there a mechanism to measure each particles separately? And for Dr. Mustafa, have you worked with other standard fabrication processes? I mean, after R&D researchers develop their process on these 0.5-inch wafers, they need to go, for example, for larger scale and produce it with mass production. Is there any standard processes, for example, for MEMS, SOI MEMS, or other techniques? Thank you.
Is that Dr. Murad?
Yeah, so thank you for the question. It's a very good question. So you are looking in the future. We did, so the first product that we worked on was for PM 2.5, because this is the one which there's bigger interest in. But there are interest in other applications for smaller particles. And yes, you can actually expand the channels that you create so that you get the different particles into different chambers. And then you can measure the different sizes of particles in parallel, but then the system will be bigger. So the question is really, should we do it as one system that will measure the different ones, or should we make different chips for every type of or every size of particle? But it can be technically it can be done on one chip. It's going to be a bigger one, but then technically it can be done there.
Yeah. Thank you for the question. Actually, yes, yeah, your question actually is one of an important point. How to move actually from minimal fab when you design a circuit, minimal fab, and go to the mega fab. And actually now that's what we are trying to do now, to have like a standard fabrication process that can be compatible as well with the mega fab. And we have now we are trying actually to develop this process to have any alignment and compatibility between the mega fab and minimal fab. Not yet, it's still under development, and it isn't actually in our plan now. But currently, what we are doing is now to do the full things by the minimal fab. But as I mentioned, we have some devices that fabricated by partially by minimal fab and mega fab. So we are trying to customize some of our rules in order to have these devices compatible with both minimal fab and mega fab.
Wait, Professor. The microphone, please.
Thank you very much for unbelievable presentations. I have a question for Murad and one for Mustafa. And I'm just trying to understand, in the application that you presented, the particle sensor, which is very, very important. I come from India, I understand. In fact, I'm scared to go back right now. But what does silicon carbide, what advantage does silicon carbide play in this? I understand for aerospace, but what is the advantage there?
Yeah, it's a very good question. So I didn't mention, but you know, we started the company with this core silicon carbide technology, and we developed some sensors, like for example, high pressure sensors with silicon carbide. We also developed some sensors for medical application where you use silicon carbide to coat, because you know it's a very inert material and it's very good, you know, for implants and so on. But for this specific one, there's no silicon carbide. Actually, the sensor itself is done with a standard piezo MEMS technology. There's no silicon carbide there. Yeah.
Okay, thank you. Mustafa, thank you. It was a fantastic presentation. I didn't realize what could be done. I was just wondering, one question, Mustafa, is why did you choose, it's a follow-up question that was asked, why did you choose 1/2 inch as your, it seems, and if you do 1/2 inch, how do you move a 1/2 inch wafer into a mega fab and then back into a minimal fab? This is a little confusing.
Okay. Actually, yeah, I heard this question many times. Yeah. Why we select non-standard wafer size? Actually, the objective here is to minimize the silicon wafer in order to reduce the waste of the silicon, and you can fabricate only few chips instead of having a big wafer. Another constraint regarding the unit itself, when you talk about 12-inch, it required more space. While our devices that we have, as you can see, the unit, it's like almost like this size. That's one of the reasons that we have that small wafer size. Regarding the compatibility between the mega fab and the minimal fab, yes, that's one of the concerns now that we are now targeting now. How to can have a compatible design rule even, and how to can move from the chip from minimal fab to do more processes. That's one of the concerns now, the consortium now is trying to handle. But actually, the ultimate objective of minimal fab is to have a full semiconductor system. No need to go from minimal fab and mega fab. Otherwise, there's no clear advantage. If you still need the mega fab, then what's the point of having a minimal fab?
Thank you.
Yeah. Actually, I have a question. So you have a 1/2 inch wafer. How do you put it in a mega fab 8-inch? I think this was the question, right?
Yeah, that's a question. Yeah.
So how do you do it?
Yeah, actually, as I mentioned, the intention here in minimal fab is not to have both the fabrication in minimal fab and mega fab. And we need to have a full system that can do the all fabrication for low volume production. So there is maybe some confusion that we need a minimal fab and mega fab. That's not true. And our intention is to have the minimal fab as a full fabrication system. It can do from A to Z.
Okay, we need to stop here. I'm sorry. Thank you for everyone. Thank you for the speakers. And let's go to the next session.
Thank you all. Efficient photovoltaics. He is the co-author of 2 books, Distinguished Professor for Electrical and Computer Engineering at Purdue University, has a PhD from the University of Illinois. Please welcome Professor Xiaochek Roy.
All right. So thank you for the invitation. What I'm going to do today is talk about rethinking computing with neuro-inspired learning, going all the way from algorithms architecture to neuromimetic devices. So I'll be changing gear a little bit, talking more about AI and AI hardware. So we have seen AI making a huge amount of progress in the recent past. So you can't even open today any technical news which doesn't talk about AI. That includes, for example, DeepMind's AlphaFold 2, Waymo opens driverless robotaxi service to public in Phoenix, and so on. But the question, of course, is at what cost? See, if I were to really look at deep learning and try to look at the machine learning saga, that sort of started back in 1997 when Deep Blue beat Kasparov quite handsomely. And then back in 2011, Watson winning against the Jeopardy masters. And finally, with deep learning, the advent of deep learning 2012, that was really fueled by hardware like GPUs and so on. We had this great news in 2016 where AlphaGo beating Lee Sedol. Interestingly enough, today it's going to be very, very difficult to beat the computers. Both in space, chess, or in, for example, Go and other games. But the question, of course, is at what cost? So if I were to really look at the human brain, that probably does things at about 20 watts or so. That's a number that we get to hear. Whereas if I were to really look at what's happening with these mega machines that are used for beating these humans, they consume about 200 to 300,000 watts of power consumption. That's humongous. And at the same time, we are certainly moving forward. Algorithms are getting closer and closer to what the brain does. And, but the hardware cost, if you were to really look at that, that's moving further and farther away. And certainly our aspirations have grown faster than what the technology can satisfy them. So if I were to really look at the compute demand of AI, and in this particular case, I actually looked at image classification problems, language processing, and so on, and looked at training some of these applications. It turns out, if I were to look at the number of operations required to do, for example, NAS, which is network architecture synthesis, turns out they're in the range of 10 to the 21 operations. So that's a humongous number of operations that you do. So correspondingly, if you look at the carbon footprint, that's also very, very large. So to that effect, there's a need to really think about rethinking these computations to be able to reduce the energy consumption. Now, I also looked at the efficiency gap, looking at, for example, edge applications. And we took an example of a case study of object recognition in a smart glass with state-of-the-art accelerator. And that included actually a Google Edge TPU. So if I were to really look at using these smart glasses to recognize, for example, human face, using an architecture called the RetinaNet DNN on a smart glass, and we did an analysis of that, and we found that the battery life, or the time to die for the battery is going to be less than an hour. In fact, under ideal conditions, it's about an hour. And if you really consider all the non-idealities that are available, it turns out the battery is not going to last more than half an hour or so. So the question, of course, is that where are these inefficiencies coming from? We certainly have an existential proof that the brain is efficient. And if you consider that, turns out where these inefficiencies come from, we certainly don't know the exact algorithms in the brain, right? The training and the inference algorithms. The hardware architecture of the brain certainly is quite different from what the hardware architecture that we use for CPUs and GPUs. The brain doesn't have on one side memory, on the other side of it a processing unit. Turns out that the traffic from the memory to the processing unit and back, that can be quite humongous. That's called the von Neumann bottleneck or the memory wall. So that's another problem. And finally, the circuits and devices that we're using. We certainly today use CMOS devices for building some of these neurons and synapses. Turns out, while they're very efficient in building, for example, switches, may not be the greatest of switches. There's a good amount of leakage available, but they're good enough to really build digital computation. Whereas on the other side of it, if I were to build, for example, neuromimetic devices like the neurons and synapses, there's a need for thinking about, do we need to go beyond the CMOS technology and so on. So far, I've talked about the compute demand of AI. It turns out there are other issues. Can I learn with less data? That's another problem that AI faces today. There are certainly problems with generalization and robustness, and you might have seen some of these problems. For example, in the bottom, I'm showing actually two macaws. On the left, the macaw is what is recognized by my AI algorithm to be a macaw with a very high confidence. And then I added up a little bit of a noise to that macaw. And once I add that noise, that's crafted noise, and I add that to that image, it turns out the macaw that I'm showing on the right, it still looks very much to the human eye like a macaw. However, my system now predicts with a very high confidence it's a bookcase. I could have made it look actually like a cat or a dog. So it basically shows that the systems do have a robustness problem. And finally, there's something that today's AI system have a problem with, which is continually learn. Right? We humans are really good at continually learning and forgetting things which are not so important. However, today's systems, when they keep on learning, task 1 followed by task 2 followed by task 3, turns out that you actually end up forgetting task 1, we end up learning task 3, unless you mix up all these tasks together and learn. I'm not going to talk about much of these, learning with less data or generalization or lifelong learning. I'm going to really focus on the compute demand of AI, and in particular, actually, how we can reduce the energy consumption. So in order to reduce the energy consumption, there's a need to really think about the proper learning algorithms and the network architecture that I use. Again, as I mentioned, that the network architecture that the brain uses is quite probably different from the network architectures that we are going to be looking at, loosely from the neuromorphic computing point of view. The hardware architecture, as I mentioned, again, quite different from the CPUs and the GPUs that we have today in the brain. And finally, the circuits and devices are quite different too. So question, of course, is can we take some cues from the brain? So what are the different cues that we can take? Certainly, there are different kinds of neuron models that are available. The Hodgkin-Huxley model, or for example, the leaky integrate and fire kind of model, or in fact, even a simplified model like a ReLU or a sigmoid kind of model. The learning algorithms, so whatever little that we know, the brain possibly doesn't use a backpropagation, but it turns out that the way the computer scientists use backpropagation today, there's a good theory behind it, and we can come up with an optimization and a solution in reasonably quick time. But also on the other side of it, people have looked at the possibility of using, for example, localized learning that has been seen in, for example, the hippocampus of rats. That includes, for example, spike timing dependent plasticity-based learning or other localized learning. The network topology that the brain uses possibly has recurrent connections, but in fact, for inference purposes, it turns out that the network architectures of the number of layers are actually probably no more than 6 or 7, but today's deep learning uses probably hundreds of layers of these neurons and synapses. And finally, the computing principles of the brain certainly are quite different, as I mentioned. They do computations with spikes, and at the same time, the computations are not synchronous. They're asynchronous in nature. So with that in mind, the question is that can I really think of coming up with a hardware system architecture or devices that can do these computations effectively, these neuromorphic algorithms that we're developing that they can do effectively on a device on the hardware fabric that one can potentially build. Let's try to look at the hardware fabric one more time. I'm not going to go into the details of the algorithm part of it. Is it possible that I come up with circuits and architecture that can efficiently implement the algorithms and possibly embody the computing principles of the brain? So to that effect, there are certainly today multi-core GPUs and accelerators that have been developed. However, they don't really look at, as I mentioned earlier, they all have the von Neumann computing architecture. So what's a von Neumann computing architecture? We have the CPU on one side and the memory on the other side, and there's a good amount of traffic, as I mentioned, between the memory and the CPUs. And that's a huge bottleneck today in today's computation. The question, of course, is it possible then, just like as we do in the brain, again, we don't understand it quite well, but is it possible that I do the computations in the memory itself? Is it possible that I have the data in the memory and do the computation in the memory itself in some interesting ways, so that the traffic that we have from the memory to the CPU and back can be optimized? So to that effect, there's a need to think about rethink computations with near or in-memory computing. There's a possibility that you can do different kinds of approximations and potentially use a stochastic hardware. So what kind of approximations that we can use? We certainly know that brain is error resilient in a lot of ways and can potentially do computations with approximations or, in fact, even having stochasticity. Stochasticity in a lot of ways can potentially help in getting better generalization. So as an example, when I talk about approximations, 10 plus 10 certainly is equal to 20. However, if I say that, hey, 10 plus 10, I'm going to be satisfied with 10 plus 10 to be 19 or 21, provided the hardware that I get is really energy efficient, then it does make sense to use such approximations in these computations. So that's, interestingly, a mathematically very interesting problem. And one can use such approximations to do computations. And when you train your hardware or when you train your system, you can take some of these approximations into account. And again, as I mentioned, that rather than doing, for example, synchronous computations, is it possible that I do event-driven computations? Turns out when we look at neuromorphic hardware and look at the number of spikes that are there in the brain, for computation, they're quite rare. So if I can do the computations only when there are spikes available, then of course I can reduce my computation efficiency. And finally, can I really look at devices that can mimic the neuron and the synaptic operations more efficiently rather than using CMOS? So to that effect, again, today we are in multi-cores and GPUs and different kinds of accelerators. So what one can potentially do is look at in-memory computing, approximate and stochastic hardware, and using these neuromimetic devices can potentially bridge the gap or close the gap that we have between the energy consumption of today's hardware and the brain. Now here I'm showing basically different kinds of colored devices, both literally and figuratively. Some of these devices are quite interesting. On the left corner, I'm showing a potential ferroelectric transistor that can potentially be used, for example, as a neuron or a synapse. And on the right side of it, I'm showing a skyrmionic device, which again can be used as a integrate and fire neuron. But more recently, there's been a good amount of work that has been done in the area of, for example, magnetic tunnel junctions, in particular, actually, magnetic tunnel junction with a heavy metal at the bottom, or, for example, the RRAMs and the PC RAMs, and they can effectively, implement neuron and the synaptic functionalities. Again, what I'm going to do is I'm going to focus on some of these devices and see the possibilities of getting a hardware that is efficient and can potentially lead to a good amount of energy efficiency. So if I have to really compare some of these devices, in particular the PCM, RRAMs, and the magnetic tunnel junctions, and compare that to the CMOS memories, and by the way, these devices are non-volatile, whereas CMOS is certainly a volatile memory device, one can look at different capabilities, the storage density, can I implement multi-level cells? For example, a PCM or an RRAM can potentially implement multi-bits in the cell itself. The question, of course, is that useful? The storage density can be quite high in that case. CMOS certainly has a lot lower storage density. Another important thing that plays a role is the R-on to R-off ratio. So whereas the R-on to R-off ratio for PCMs and RRAMs are quite high, the magnetic tunnel junctions, today the TMR is quite low, and that can potentially be a problem. Non-volatility is certainly useful, but at the end of it, the cell area, which is I'm showing here for PCMs of the order about 16F squared, whereas the CMOS is of the order about 160F squared or so. That's a huge difference. And that can potentially lead to various advantages that we can have. Going to the DRAM, this traffic to the DRAM is quite useful. Right energy, that actually plays an interesting role in all these in neuromorphic applications. It turns out the PCMs and the RRAMs certainly has a lot higher right energy. Anytime the barrier height is high, right energy is going to be higher. Whereas CMOS certainly has a lot lower right energy, and the magnetic tunnel junctions, again, somewhere in between. Endurance turns out to be quite an important issue in some of these analyses, and the reason is that, PCMs and RRAMs have a lot lower endurance, both write and read endurance, compared to, of course, the CMOS and the magnetic tunnel junction technology. And that leads to the issue of, can I use, for example, PCM and RRAMs for training? Apparently not. You might have to potentially use CMOS or, in fact, MTJs for the training architectures. So again, these are the important issues that one has to certainly look at when you build the next generation of AI hardware. Now let's look at in-memory computing. As I mentioned, that can potentially lead to a good amount of improvement in energy consumption. So in general, if I were to really look at today's memory, the best CMOS caches that are on-chip memories, usually what we do is we turn on one word line, and turning on one word line with having peripherals to be sense amplifiers, one can do reading operations. However, if I'm able to turn on multiple word lines, in particular actually 2 word lines in this particular case that I'm showing, it's possible to do logical operations or vector operations. Now it turns out that you may not directly be able to do that. You might have to change the topology of the memory. And the reason why that is required is otherwise there might be, for a 6-transistor cell, there might be a direct path from VDD to ground. Again, the cost that you end up paying in that case is having larger peripheral circuitry. Now, you can be a little more greedy and say, hey, can I turn on multiple word lines simultaneously in these new kind of memories? And it turns out if you do that, you can do matrix vector multiplication operation. Now, that's interesting because the matrix vector multiplication operation turns out is a major operation that you then end up doing in most of these machine learning applications. The price that you pay is basically at the bottom that I'm showing is really the peripheral circuitry that I need. Unfortunately, now the computations that you're doing is in the analog domain. And when you start going into the analog domain, you end up adding noise. And so far in the industry, there hasn't really been a digital chip which uses a lot of analog circuitry. So again, certainly industries are quite scared of that, because that can potentially lead to lower accuracy and at the same time possibly lower yield. To that effect, there's a need for really having an analog to digital converter that I'm showing at the bottom, right, the peripheral circuitry. And that we'll see is going to cost you quite a bit, this analog to digital converters. So though you're able to do matrix vector multiplication operations, turns out that the cost can potentially be large unless you take care of some of these problems. So the kind of technology certainly one can use for these in-memory computing could be the non-volatile memories. One can also embed, for example, a ROM into a RAM, and that's I'm not going to be talking much about that, but it's possible to do that with very little cost, and that can also lead to in-memory computations. And finally, SRAM can certainly be used. However, SRAM is going to cost you in terms of area, a lot more area. So if I were to now just go and look into these non-volatile NVM-based computations, and I'm going to call those to be crossbars, it turns out what one can do is you can have these inputs which are coming in, could be analog values, and the output of these crossbars where the crossbar element are going to be some of these interesting devices that I'm going to be talking about. Could be CMOS also. They end up being, doing these matrix vector multiplication. So how do I do matrix vector multiplication? So I have these inputs which are coming in, which are analog values. And the output that I get on the vertical lines are the summation of, by Ohm's law, by summation of some, VI times GI, GI being the conductance of these devices. So how about these devices? Can these devices be, for example, PCMs, RRAMs, or different kinds of, memories? They could be actually domain wall-based, magnetic tunnel junctions or SOT-based tunnel junctions and so on. But any one of these, devices can potentially be used in such a crossbar and for doing this matrix vector multiplication of the dot product computations. Few things which are important. You need two terminal, selected devices or transistors in there. And the holy grail of such crossbar-based computations is to have a effectively two-terminal selector device. But if you don't have one, you can replace that with a standard transistor. Now you can take these devices and these matrix vector computation unit, and you need a large number of those. Because of these non-idealities, you may not be able to have these crossbars to be more than a certain size, maybe 128 cross 128 crossbar. That's not enough. But if you take these crossbars, which are analog matrix vector multiplication unit, they can be repeated, and you can put them in an architecture with a network on a cheap architecture, and they can potentially do computations. Now, what's the catch? Again, you need these analog to digital converters at the output of these crossbars. And they can cost you in terms of power consumption. Question, can I use CMOS devices? The answer is yes. You can replace some of these devices with CMOS. I'm showing an 8T cell over there. Again, the cost is in terms of quite a bit larger area. So one can potentially think of a spatial architecture where you have these cores, but that I'm showing at the bottom. Each of those cores contains these crossbars. And multiple of these cores end up being into a tile. You certainly need some CMOS circuitry and some memory to do these other kinds of computations, which are not matrix vector multiplication type of computations. And then one can think of a network on a chip architecture, which looks somewhat like this. And it's a massively parallel architecture and can potentially be quite efficient for machine learning applications. Now, a few things which are also important. The things are not that simple. Turns out that when I look at the crossbars that I just mentioned earlier, few things which are important, that each of those devices would potentially implement multiple bits. So now if I have to really think about a PCM or an RRAM that can implement, let's say I need to implement 4 bits and my device may not be able to implement 4 bits. So what do I do in that case? I do something called bit slicing or the weight slicing. So if I have to implement 4 bits and my device can implement 2 bits, then I need 2 crossbars to do that. Also, at the same time, I do something called input bit streaming. And the reason why that is done, I earlier showed analog values. The reason I do bit streaming is so that I can reduce the noise in those. So bit slicing, which is weight slicing and input streaming, would enable low precision crossbars to do, and low precision digital to analog converters to do high precision MVMUs, which is matrix vector multiplication units. So a few other things which are also important, that when I really have these large crossbars, few things turn out to be quite important. The NVM crossbars have various non-idealities. So what are these non-idealities? They include certainly parasitics that are going to be there in the crossbar, the line resistance of these crossbars. You have also the non-idealities of these devices. They may not be linear, right? And the R on to R of ratio, you'd like to have it to be as large as possible, but they might be smaller. So these non-idealities introduce varying amount of functional errors on different voltage and conductance level. So what I'm showing on the right is ideal versus non-ideal current that you're going to see. The ideal current is going to be that 45-degree line, which is shown as ideal. And the non-ideal I'm showing actually after an implementation, there's a good amount of variation that you see. So at the end of it, these non-idealities would lead to the crossbar size that I can implement. The larger the crossbar, the more the non-idealities is going to be, and that can introduce more errors. So the size of the crossbar turns out to be important. And finally, at the end of it, the larger crossbar also, in some ways, lead to actually a larger area for the A to D converters. As I mentioned earlier, those can potentially be the bottlenecks, and the energy consumption. The energy consumption of this whole architecture is now dominated by the analog to digital converter energy. So in order to take care of that, as I mentioned earlier, one can do is, if I were to really look at a matrix vector multiplication that I'm doing on the right, I'm going to have these weights to be programmed into my memory. If they're not able to handle, and these inputs should be coming to the, as analog inputs to the, as I've shown earlier. However, as I mentioned, that each of those bits may not be representable directly into that crossbar. So I need multiple crossbars, and I have to implement those across multiple crossbars. And I also need to do this bit streaming that is required in order to actually reduce the noise that I'd have otherwise in the crossbars. Now, if I do that, as I mentioned earlier, that one can potentially get high precision matrix vector multiplication units. If I were to really look at, for example, a machine learning workload, and that may require a huge multiplication of these matrix vector units. Again, without going into the details of it, one can do a convolutional neural network, flatten the inputs, and do these large output matrices into a 3D tensor. And that can be represented now in terms of the weight matrices on memory arrays. And each of those weight matrices would look somewhat like this that I showed in the previous diagram, where there's going to be these crossbars. And you're limited in size to what each of those crossbars can be because of the non-idealities. And at the end of it, each of those crossbars are going to be associated with some ADCs. And finally, if I had to really look at this entire matrix multiplication that I need to do, I need to then, at the end of it, accumulate the results of all these crossbars to be able to do the final computations. So it's not quite as easy as I mentioned it earlier. So there's a need for really thinking about how to do that. Proper modeling and simulation ecosystem is required. So going all the way from device models to circuit models to crossbar models, and finally, being able to do these computations of the functional modeling at the architectural level. Now, if I do that, turns out, I'm skipping a few steps. One can try to see what kind of results I can get. So what we did is we looked at different types of machine learning applications. In particular, actually, deep neural networks, the wide neural networks, the CNNs, which are basically the convolutional neural networks, and tried to compare that, this new architecture with these devices, with the Skylake and the Pascal, which are basically these NVIDIA GPU processors. Turns out if you do an analysis of it, and its potential that you can get improvements of the order about 100 to 1000x in terms of energy consumption, even with the kind of ADCs that we talked about. Now, it's possible then to really actually reduce the ADC cost effectively later on and say, hey, can I really, when I'm learning, when I'm training my architecture, or when I'm training my data set, is it possible that I train also for the non-idealities of the underlying hardware architecture? The non-idealities coming from the analog noise may not be learnable. However, the quantization that I do with ADCs are learnable, and hence the ADC can actually reduce, rather than using 6 or 7-bit ADCs, one can potentially go down to 2 or 3-bit ADCs, and that can still give you a good amount of improvement, while at the same time, you learn the non-idealities of the quantization noise. One can certainly use also CMOS, and in this particular case, I'm showing an example of a CMOS-based hardware using in-memory computing, in particular actually for spiking neural networks. Compared to the standard neural networks, the spiking neural networks are a little bit different. The reason why they're different is they use these spikes rather than analog values of input signals. It's kind of trying to mimic what the brain does to a certain extent, but there's few bottlenecks that you have in a spiking network. Compared to, for example, a standard neural network, here you also have, if you're using a leaky integrate and fire kind of neuron, which is closer to what the Hodgkin-Huxley model is, turns out you have to really think about updating the not only the weights when you're training, but also at the same time will be updating the membrane potential. Every time an input comes in, the membrane potential gets updated, and when the membrane potential reaches a particular threshold, there's a spike that is produced. So that also tells me that every time I do computation, I have to get data from the memory, right, which is the membrane potential, update it, and put it back in the memory. Again, that is inefficient, so rather than doing that, is it possible that I actually have, in the memory itself, do these computations, both the weight updates and the membrane potential updates in the memory itself. So again, one can potentially think of these kind of memory that I talked about, where you can have a fused weight memory and the membrane potential memory together, so that the updates can be done in the memory itself. You don't go out of the memory, you stay all the time in the memory itself and do the computations. If you do that, and again, without going into the details of it, this is actually implemented using the standard 80 kind of bit cells. Okay? If I do the computations with these, turns out, and again, this was implemented in a 65 nanometer technology with these 10 TSRAM cells. And again, remember that our RAMs or the STTM RAMs are going to be a lot more suitable. But if I'm able to do that, it is a prototype chip fabricated in 65 nanometer process, shows about 1 TOPS per watt at 850 millivolts and 200 megahertz of operation. Again, the demonstration was done for spiking neural networks working on sentiment analysis. For example, the IMDb data set, which basically looks at sentiments of different movies and all. Turns out you can go further down the road and say, hey, can I do computations not only in the memory, standard caches, can I do it in DRAMs and other kinds of memories? And turns out, again, going into without the details of it, you can do majority functions in the memory and in the DRAM by turning on a few word lines together. And this is actually showing a memory cell which can actually do not only, you can enable multiple cells to do majority operations in the DRAM cell itself. One can also do, without, again, going into the details of it, one can calculate, once you're able to do the majority functions, you can also do carry functions and carry out bar functions. And if you do that, again, you're able to do now addition operations within the memory itself. And a few more changes to it. Actually, you can do matrix vector multiplication operations. And this is actually showing how, by having some extra compute rows, and not much, only about 9 extra compute rows, you're able to do the computations in the DRAM itself. And this is an example of doing computations in a DRAM for K nearest neighbor problem, which is actually an important problem in machine learning applications. You check the K closest samples and query vector assigned to the group that holds a majority among the K samples. And this is, again, showing a host processor with the main memory and the DRAM computing to be able to do these computations, and shows that if you were to do some of these computations, and you can divide this computation properly into DRAM and the main memory, and do in-memory computing in DRAMs, you can get about 12x performance improvement. So here's some parting thoughts. I really believe that the future workloads would require rethinking of energy-efficient hardware architecture. There are different kinds of interesting devices one can look at. And while CMOS is still the technology of choice, it's certainly some of these neuromimetic devices that I talked about has some interesting possibilities. Looking at some of these devices in memory and near memory computing, or rather memories being dumb bits, can I make memories to be intelligent? So having intelligent memories can potentially be quite useful. And finally, putting these things together into a heterogeneous integration can potentially improve the energy efficiency of some of these implementations a lot. So our algorithm hardware co-design, I believe, guided by biological principles, can be the pathway for next generation neural computing. So that's all I have. These are some acknowledgement for our sponsors. Thank you.
Thank you, Professor Roy. Professor at King Abdulaziz City for Science and Technology, please welcome Professor Abdulrahman Al-Badri.
Assalamu alaikum. Good morning. Thank you for the introduction, and I'd like to thank the organizers for the invitation. Today I'm going to talk about multi-junction solar cells based on gallium arsenide materials. As an outlines for the presentation, first of all, I would like to talk about the current world record. Then we'll talk about two technologies that we've been working on. The first one is the lattice matched technology to build multi-junction solar cells. And out of that technology, we built flexible structures. Then we use another technology, which is the dilute nitride technology, to build lattice matched and current matched solar cells. And we use that technology to build CPV models, and we will use it for space applications. The world record, this is the famous table, and you can see the top of the table shows the highest efficiency achieved currently, which is achieved by Enrel. They used 6 junction solar cells, and they got about 47% under concentration. They used 143 sun concentration. Without concentration, they got 39. So this is the highest efficiency ever. So we are reaching the what we call the golden number, which is the 50% efficiency. There are many technologies to build multi-junction solar cells. First of all is the traditional one, which is you build your structures on germanium wafer. Then you have the Indian gas and the NGAB, the Indian gallium phosphide. They are lattice matched. This is the easy one. So germanium and the Indian gallium arsenide, the Indian gallium phosphide is lattice matched, and you got a 3-junction solar cells. The problem is the germanium drives more current because the band gap is less. So this is the constraints of this structure. To mitigate this problem, the community moved to the metamorphic structure, where they try to balance the current. So they use the germanium wafer, then we have the step-graded buffer to build lattice mismatched indium gallium arsenide with a band gap of 1.3 and the N gap of 1.8. So the current is more matched, but the voltage drops a little bit. But we are limited in these two structures to 3 junctions. We cannot build more than 3 junctions. To go to 4 junctions and beyond, you have to go inverted metamorphic, which Enrel used for their 6-junction solar cells. So you have to invert metamorphic. What do you do with the inverted metamorphic? You start with the top, which is the Indian gallium phosphide, the 1.88. You start the growth in germanium or in gallium arsenide. You do it in gallium arsenide substrates. You have indium gallium phosphide, then indium gallium arsenides. They are lattice matched with the wafer. Then you still have the step graded to get the 1.0 electron volt band gap. So you cannot get it unless you have lattice mismatch in this case. Then you flip it, then you bond it to a carrier to be used as complete structure. The last one is the dilute nitride technology. It's an interesting technology. So in this case, they overcome the problem with having 1.0 electron volt band gap semiconductor for the gallium arsenide alloys by inserting dilute nitride material. So little of nitrogen can move the band gap while the lattice is still matched. So the highlighted, the traditional and the dilute, this is what we have used at CAXT recently. This is the traditional multi-junction. We used in germanium in collaboration with IBM. we used MOCVD reactors to build the structures. And the TM images you can see here shows the top cells and the middle cells and the bottom cells. So you can see no defects between the layers, and the junction is very, very good. Then this is, we do some characterization for the 3-junction cells. The XRD in the bottom right, it's between the germanium wafer and the top wafer, which is the top cell, the indium gallium phosphide. It's aligned, so there is no mismatch between these two. The AFM shows a smooth surface for the top surface. And we can see here the SIMS data. We are showing the materials inside the 3 junctions, and you can see abrupt transition at the junctions. We use the traditional technology to build 3-junction solar cells to have flexible solar cells. This is our main focus. How we can use, or how can we achieve flexible solar cells? We used what we call controlled spalling technologies. And in controlled spalling technologies, we have the triple junction solar cells. Then we have, we deposit tensile layers. Usually, it's a metal layers, usually use nickel. Then we have the flexible handle tape, the number B. In this case, the tensile layer force a tensile stress on the substrate. Then there is a shear stress. So when the shear stress, when the tensile stress is, or the top layer is tensile, it will initiate the shear stress inside the substrate. As you can see in C, the shear stress is 0. So to keep it 0, the trajectory will be horizontal to the surface, and we get a smooth films. Then we bond it to silicon substrate. Then we remove the Kapton tape or the UV tape, and we remove the nickel material by nickel etchant. This is the graph in the left, shows us how much stressor thickness we have to build, we have to deposit to get the certain thickness. So for our case, we use 30 in the left side, 20 micrometer of nickel. So in this case, we achieved about 38 depth in the fracture. So 38 covers all of the triple junctions that we have. So this is more than what we need. And it depends also on the stress, as you can see in the bottom, which is affected by temperature. But we are using our technology, our method at room temperature. Here we are comparing the bulk 3-junction solar cells with the flexible solar cells that we achieved using the spalling technology. And you can see in the top right is the final wafer, and we divided to many cells. We tested the cells, and we got the results. So we didn't lose much of the performance of our structures after we do the spalling. So we got the bulk 30%, which is a very good number for the traditional multi-junction cells. And after spalling, we got 28.7. As you can see in the left side, the external quantum efficiency shows that the bottom junction is severely affected by the spalling, which is understandable because it's the latest or the bottom junctions next to the fracture that we initiated. We moved now to the second technology, which is dilute nitride technologies. As you can see in the right top, there is a missing materials between the germanium and the gallium arsenide. So between 0.7 and till 1.4 electron volt, there is no material that lattice matched the gallium arsenide and its alloys material. So this is overcame by using dilute nitride, as you can see in the left. By adding dilute nitride, you can get the Boeing curve. So we add dilute nitride, but the band gap or the lattice match is going down. So we get band gap tuning while keeping the lattice match. So we cover the band gap or the missing gap between gallium arsenide and germanium. And in this case, the only way to get semiconductor with the 1.0 band gap is by using the, which is lattice match with the gallium arsenide, is by using dilute nitride technology. Silicon will be okay, but silicon is lattice mismatch with the gallium arsenide, so it's hard to build gallium arsenide in silicon. So this is the structure. We did it in collaboration with the Solar Junction, and we have our MBE now. We did some initial growth. The structure, as you can see here, dilute gallium arsenide built in gallium substrates. We don't need germanium in this case because this is 3-junction solar cells. Then gallium arsenide and indium gallium phosphide. So the current is matched here. So we are getting much more currents, and we have higher voltage. As you can see in the left, we measured this structure under 1600 sun using our flash tester sun simulator, and we got these results. So we have about 41% efficiency at 1600 sun. So it's the highest concentration used in the community. Usually they use less concentration to get higher efficiency. And the quantum efficiency for the 3 junctions showing good results, and the currents is a little bit match in this case. We used this paper which by the Demorth from in the CBV system, or the CBV conference, BCVC. They showed that the spectrum changes along with the graphical location, with time, with water vapor, and different things. So the spectrum that we have here in Riyadh, for example, it's different than spectrum than have in other cities. So this is motivate us to test the triple junctions that we built at different locations in Saudi Arabia. So we built our CBV modules. You can see in the right side. We have 16 cells, 4x4. We built our CBV modules to get 1600 sun, and then we tested it at different locations in western part of Saudi Arabia and in Riyadh, and we get this result. So we proved that different locations, different spectrums affects the efficiency of the solar cells. So this brings us that tuning the structures of the 3 junctions is very important for each location. So what's working in Saudi Arabia maybe not working in other locations for the same for the same structures. So you have to be careful about this and tune it accordingly. So this is for the 16 cells on the right side, and we also did one single modules. We have just one cells and concentrated with 1600 suns, and we get the results. As you can see here, in Taif is the DNI is less than in Diba. Diba is the northwestern of Saudi Arabia. So the DNI is the highest. So we got one of the best results in Dubai. And Taif is the DNI is less. And I should mention that concentrated solar cells requires normal radiance. So we cannot have the diffused light, so you have to have a direct light to the system. So you have to have a very good tracker with the system. Next, using the same structures, there was a call by the United Nations and the Chinese Space Agency to do some experiments in space. So we proposed our experiment and it was selected. So we are preparing right now a panel consisting of 3-junction and 4-junction cells to be tested in the low Earth orbit. So the goal is to assess the radiation effects in 3 and 4 junctions. I should mention that current space systems, satellite, using still 3-junction cells. No one is using 4-junction yet, because the 4-junction that's built is using bonding wafers. So bonding wafers, it may have problem in space. So we are testing our 3 and 4. We are testing both. We have got some cells from collaborator, and we have our dilute nitride 3 junctions, and we have 4-junction cells. All of them will be tested in space next year. And with this data that we will get from the space, we will be able to tune the structure that we have to mitigate the radiation effects, to build a radiation hardening design system for space. As you see here, whichever cell is the softest will control the overall cell performance. So the worst cell will compensate your performance. So in this case, we will have to build our system according to the space environment, not the ground environment. Even if we get a lower performance in ground, so we have to have the beginning of life sacrifice so that we get higher performance in space. This is some results from different groups showing how the radiation affects the solar cells. As you can see here, they use different electron source with different energy, 1 and 1.8 and 11, and they got the normalized maximum power. So you can see that there is a decrease in each of these cells. So electron and proton affect the cells, besides heavy ions as well. In the quantum efficiency, they showed they showed that the middle cell is more vulnerable to radiation. So in this case, this will allow us to tune the middle cell more to get more hardening structure. Yeah, the multi-junction solar cells is a minority carrier devices. So it's mostly affected by the displacement damage. So the radiation effects, proton, high electrons, and ions will affect the lattice of the structure and damage the cell, will result affect the lifetime of the minority carriers inside the device. So this is the most important for these devices. Yeah, so in conclusions, we mentioned in this talk our activities. We started with the traditional lattice match, which is like standard 3-junction solar cells. We used it just mainly to have the flexible solar cells. This was our main focus for using the traditional ones. Then we moved to dilute nitride because it has more we use the dilute nitride to develop the CBV and the space cells. So it's much better than the other technologies. And as I said, hopefully next year we'll send our cells in space and start collecting some data. And thank you very much for Excellent.
Thank you, Professor Abdurrahman. Materials Science and Engineering Professor, King Abdullah University of Science and Technology, please welcome Professor Chua Jang Jan.
Hello, everyone. It's my honor to be here to deliver my first official talk in Saudi Arabia. I just joined KAUST 3 months ago, and I know my first name is difficult to pronounce, but my last name happens to be gallium nitride. But today I will discuss a different topic, radiative cooling from energy sustainability to semiconductor. So in the first part, I will explain how radiative cooling is considered as an energy sustainability technology, and then I will discuss how to implement this technology for future semiconductors. So this is a temperature distribution created by NASA in 2005. So according to this map, we can recognize that because of the concentrated and crowded human activities in big cities, the average temperature in urban areas is obviously higher than rural areas. This effect is called urban heat island effect. Okay, so because of this human activity, so the air conditioning cooling is actually in higher demand in these big cities. According to US DOE's estimation, in a typical building in the US, the electricity consumption of air conditioning is approximately 15% of the overall energy consumption by a building. This percentage is much higher in tropical areas. For example, in Saudi Arabia, it was estimated that this percentage is between 50% to 70%. As a result, a higher energy efficiency technology is highly desired. So in the past years, radiative cooling is considered as such a sustainable cooling technology. So here I will first explain what is radiative cooling. So this is a typical thermal imager. Many of you probably already saw these photos taken by a thermal camera. Thermal camera actually recorded the thermal emission of objects. Another example, when we stand next to a wildfire, even there is no air blowing towards your face, you still feel warm because of thermal radiation. In this situation, the thermal energy will be transferred from high temperature emitter to low temperature receiver. Radiative cooling follows the same principle. In this situation, the objects on the planet is a high temperature emitter. The outer space is a low temperature receiver. As long as the thermal emission can go through the atmosphere, then we will enable radiative cooling channel. So now let's look at the atmosphere transmission window. We can see the blue shaded region. In the wavelength range from 8 micron to 14 micron, there is a high transmission window of the atmosphere. Therefore, the first task for radiative cooling is to enhance the thermal emission in this transparent window. However, the actual challenge is during daytime, we still have very strong sunlight. Therefore, the second task is to minimize the solar heating effect. In the past years, this is a very hot topic. A lot of groups published advanced materials to realize daytime radiative cooling. We can see that the photo of these materials, most of the materials are white in color because they want to block the sunlight by scattering them back. Therefore, the solar heating effect will be minimized. Then they enhance the thermal radiation, they can realize radiative cooling. in the past years, my group focused on developing a transparent coating that can be find a lot of other applications for radiator cooling. So we create a kind of transparent coating that can be applied to any surface. We can see that using a roll-to-roll coating material technology, this coating can be easily fabricated over large areas. So next, I will show you a short video, which is the most important video. So please help me to play this video to show this simple radiator cooling effect. Is this possible? Yes, please click. Yeah. Oh, no. Please go back to the previous slide. Yeah, click the play button. Yes, that one, yeah. So here is our coated aluminum foil with this transparent coating. We just place this aluminum foil into a thermal isolating box to mimic our house, for example. In this box, we have two temperature probes, one inside the box under the aluminum foil, and the second one is outside the box. After that, we introduce a thin film plastic to seal the box. Then we prevent the air effect. So after that, if you see some cooling, this is not introduced by air, it's introduced by thermal radiation. So the experiment setup is already done. So now we will show you the experiment result. We have two temperature readings. The first reading is the temperature inside the box, and the second reading is the ambient temperature. Okay, by simply placing this box on a ground facing the sky, you can see our sky is very clean at Buffalo. The temperature inside the box kept reducing, and after 15 minutes on that day, we realized a 7 degrees C temperature reduction below the ambient temperature. Okay. So by injecting a humid air into this cooled box, we can accelerate the condensation of the moisture from the air. So this is our recent work. We collected the condensed water and compare it with a commercial mist collector, and we obtained around 3 times more water collection. So this is just published last year by PNIS. And more recently, we designed an improved architecture to enhance this radiative cooling and obtained 14 degrees C temperature reduction between ambient temperature. And this work was featured as a breakthrough by Nature. So I have a startup company. We are trying to fabricate a module so that we can assemble this module on a roof so that we can enable electricity-free cooling for the future house. And in 2020 January, Nature published a short feature article. They summarized 13 breakthroughs along this topic, and 2 of them are from my group. More recently, my friend in China developed a very interesting topic. By introducing this coating on ice cream, they demonstrated the melting rate of the ice cream can be slowed down significantly. So why this is important? Okay, this gentleman will like this technology. So everyone knows as the global warming continues, the ice mountain in Arctic area will melt. So if this global warming continues, ultimately the coastal cities like Shanghai, Jeddah will be buried by water. So this is related to everyone, not just a local problem. Okay, to here, I just explained this technology as energy sustainability. Now I will explain how we can apply this technology for future semiconductors. If we placing these 2 photos together, can you see any similarity? In the crowded building area in New York City, we have a lot of heat and high demand for air conditioning. And if we scale this mega city into on a chip, as the density of the IC increases, the heat management is also very, very important. Therefore, cooling is very, very important for future semiconductors. Now I will discuss how can we apply radiated cooling for future semiconductors. 2 years ago, my collaborator at Stanford University, they published a paper titled Generating Light from Darkness. Here is their setup. They just set up a similar box as I show you in my video. They demonstrate 2 degrees C temperature reduction during nighttime. Okay? So in this situation, they introduced a thermal electric generator, make full use of this temperature difference. They have 2 degrees C from the radiated cooled box and the ambient temperature. Using this temperature difference, they drive one LED successfully. So you can imagine, it's a reversed process compared with solar cell. For solar cell, we are actually collecting solar energy. But in this situation, we are actually emitting thermal radiation to the sky. Therefore, researchers call this technology as anti-solar cell. This is a very interesting demo, but a larger impact it can be observed for actual solar panel cooling. Everyone knows that in tropical areas like Saudi Arabia, we have abundant solar energy. However, we have another challenge is the operational temperature of solar panel in this area is much, much higher than other areas. For example, in Buffalo, our average operating temperature for solar panel is only 50 degrees C to 55, but in Saudi Arabia, it can go as high as 70 degrees C. So according to the theoretical analysis, every 1 degree C temperature increase will result in the energy efficiency drop by 0.45%. Every 10 degrees C temperature increase will result in the doubled aging rate. As a result, the cooling technology is very, very important. But you can recognize those Nature white paper, published by Science or Nature, those white materials cannot be used for solar panel cooling because they will block the sunlight. So transparent coating is essential for solar cell cooling. So we are currently setting up the system and perform the outdoor test at KAUST campus. Another important topic is for LED cooling. So according to the manual on Philips light bulb, they will emphasize if you operate your LED at overheated condition, their lifetime and energy efficiency will be much lower. You will have a premature failure. So let's consider the situation, the actual operation condition for high power LED is during night. Okay, so in this situation, radiative cooling integrated with this street light is more natural because it's easier. We don't have to tackle the solar heating. We only focus on radiative cooling. So this is another area that can be applied. So my group is also working on that. So in summary, in the first section, I explained radiative cooling as an energy sustainability technology. And then we explained some potential applications by using this radiative cooling for semiconductor technologies. Actually, semiconductor lasers and a lot of high power 5G stations, currently they are facing this thermal energy, thermal management issues. So hopefully we can find more opportunities for radiative cooling. So thank you for your attention.
Hello. Yeah, I would like to thank you all, the audience and the speakers. Okay, and particularly, I would like to thank you, Professor Roy, where you took us a journey in building structure circuit structure for energy efficient neurophoric, which is a really interesting topic. I can see everybody's interested in that topic. Besides that, I'd like to thank you, Professor Abdurrahman, for informative presentation where you took us from the basic until to the advanced application in the space. You, Professor Gan, gallium arsenide nitride, well, yeah, this is very, I will always remember you for the presentation, first of all, and where it is very educating presentation. I guess everybody agrees on that, where you educate us in the topic from basic until took us to advanced application. Thank you. In this sunny, high energy, high efficient energy day, where I promise you, you will have more efficient days in the near future, here in Riyadh particularly. Please proceed with your question for our panel speakers. Any questions? Yes, go ahead, proceed.
Hi, I have a question for Professor Gan. So for the radiative cooling for PV applications, it's my understanding that module glass already has a very high emissivity in that spectral window. So is there going to be any kind of benefit over just standard module glass in terms of that cooling effect?
Sure. So this is a very good question. So currently, for the commercial solar panel, their top surface is glass. So basically glass. So glass has a transmission thermal radiation peak around 9 to 10 micron, the wavelength. Okay. However, the ideal, we didn't make a full use of the thermal radiation window of the atmosphere. So the atmosphere, the ideal situation is that we have a full ideal thermal emission from 8 to 14 micron. Therefore, we still have space to enhance this cooling effect.
Thank you. Any more questions, please? Yeah, please, go ahead. The microphone? Yeah.
So Kaushik, I have two questions. I believe I'm talking on behalf of my students. I guess they are shy to ask. So you mentioned in your talk that our colleagues in computer science are using backpropagation, while this is like mathematically good and great results. While in reality, there should be in the brain something like local learning, and some people are doing this in the context of LSTM. The question is, we have been dabbling with it for some time, and we are not getting the same level of accuracies that you would expect to get with the other techniques. So do you have any comments about that?
Yes, actually, we also tried using spike timing dependent plasticity. Difficult to apply to a larger scale circuits, and in fact, you don't get that much of an accuracy. But potentially can think of combining the two in some interesting ways to be able to do that. Again, not a whole lot is known about how things are done. Certainly, it has been observed in the hippocampus of rats back in 1998, Bu and Pai, they did that. Interestingly enough, also when we sleep, and during our deep sleep, there are connections. It's thought that the connections get strengthened. Whether there's any back propagation there or not is, potentially that happens. Don't know.
So the second question, if you don't mind. So when you talk about spiking neural network, so I mean, everyone is doing, to some degree are doing it. If you look at the brain, there are different regions have different spiking rates. And different coding techniques, like there is a burst mode, there is a rate. So these different codings have been studied extensively in the Information Theory Society about how efficient are they. But from a hardware perspective, there is not much work at all being done on actually developing these type of coding schemes and figuring out which one is better with our neural network that we are building in hardware. Any idea why this is not happening?
It has started happening to a certain extent. One of the things that you can really see is that if you think about rate coding, to me rate coding is very inefficient. Whereas if you really go with a digital representation of a signal, that's in a way a lot better representation because you don't need that many bits to represent it. Because there's an MSB, LSB, whereas this rate coding doesn't have that. So you need to represent it with good number of time steps. So to that effect, I mean, people have also looked at time-based coding. That could be actually interesting. We can limit the number of spikes, or in fact, even you can use, for example, codes like you can use the analog values of inputs, and the first layer of the neural network can be actually a spike generator. So the first layer of the neural network can really generate the spikes. You lose some sort of stochasticity in it, but certainly it's actually quite efficient in going all the way down to about 2 or in fact even 1 time step, if you can do that. And finally, going to some cameras like the DVS camera, the dynamic vision sensors, they would actually end up generating spikes when there's a relative motion between the camera and the object in question. So these are very, very low pass sensors that would actually produce spikes, positive and negative, depending on the directions that the object is moving. And those can potentially be quite effective in, for example, to be used with spiking neural networks. But in a lot of ways, if you really think about it, the spiking networks are really recurrent neural network as opposed to standard ANNs. So for sequence-to-sequence generation, those are more important. Maybe not that much for standard image applications.
Yeah, go ahead. Remember, guys, we are between people and their lunch, so we're gonna, if you see what I mean.
I would like to ask Dr. Abdulrahman about the lifespan of PV.
Yeah.
So PV is, as you know, is like currently is like one of the most important renewable energy in market. We are now like towards more or higher efficiency for commercial applications. So as you yesterday they mentioned the tandem cells for with silicon and using perovskite of silicon. As I mentioned today, the multi-junction solar cells, it's like giving us higher efficiency for space applications and for the terrestrial applications. So BV is very important energy source for our life day or everyday's needs. So and also maybe we can use like other applications as the cooling. I don't know, as we know, the BV, especially CPV, emits a lot of heat. So we try to do active cooling in the beginning, and maybe then we do passive cooling. Maybe we can get more advantage of the radiant cooling. So I don't know if I answered your questions or perovskite.
The stability of your system you're showing.
Yeah, for multi-gallium arsenide is very stable. So it's like semiconductor devices are very stable. The problem is with the perovskite. So we have other projects with the perovskite materials where the stability is an issue. So we measured it with different structures, and we got high stability, but still the stability is not in the form of having commercial perovskite cells. So we cannot see any commercial cells nowadays. But for multi-junctions, the stability is assured. And you can see it, like it's stable even in the space. So it's harsher environments. And thank you.
Thank you. Well, in this case, if there is nobody, or do you have more questions, guys? Or shall I proceed with you, please, Professor Gan? I saw the potential in the device you designed and you created. What is the next step now?
Currently, we are performing outdoor tests to demonstrate the real cooling performance in real environment. So for example, we are working with an air conditioning company. So they are performing tests to see how much electricity we can save. So based on our current feedback, they estimate radiative cooling can save up to 15% of the electricity consumed by their air conditioning. So this is the current data. So we are trying to identify the potential application in Saudi Arabia. I think this is a very suitable area. So that's why I moved from Buffalo, the snowland, to Saudi Arabia to tackle this cooling. Buffalo, we don't need to tackle the cooling. We have a lot of snow. But Saudi Arabia,
Absolutely.
this is a great opportunity for us to look for opportunities. Yeah.
I wish you all the best with your work. Professor Abdulrahman, when you mentioned that you engineer this bold layer thickness according to the need, and you touch upon a topic that the last layer, the last junction, which is close to the place where we spoil the material, and there is some deterioration and cracks because of this is just the first junction, and that's brings me to the technology which has been developed by CACS, where we can spoil material with as less as possible cracks, or possibly there are no cracks, when you spoil the material at liquid nitrogen temperature. Have you tried that? In this case, you might save the life of this third junction and brings the efficiency to a higher value.
Actually, yeah, we tried cold liquid nitrogen and cold water, but the benefit is to have room temperature spalling. This is to have repeatable and consistent technologies.
Results, yeah.
So the benefit of having room temperature is beyond expectation, and maybe we can add some sacrificial layers later on, so that we mitigate the effects in the junctions, especially for the inverted metamorphic structure, where the top cell will be grown first.
I see.
So when we grow it first, so the top cell is first grown. So in this case, maybe we can do some sacrificial layer, and when we initiate the spalling is less effective. But the one that I mentioned is like traditional structures, it's upright structures. So the bottom one is the germanium. So still the germanium. Maybe the cause of the spalling or the etching of the remaining of the germanium. So it's
debatable still. We need to consider it. Well, thank you, Professor Abdulrahman. I'll conclude this session. This is a beautiful session where I enjoyed it with our speaker and you, respected audience, with the conclusive question. In your resume, I saw so many awards, mashallah. So the very recent award was about the Distinguished Research Performance. That was in 2021, last year. Could you give us some information about this project particularly? Because I can see the research area you tackle is quite broad. So at which area that you received this award? I guess all of us are curious to know about that.
It's mostly related to basically looking across the stack, the entire stack, going all the way from algorithms to circuits and then to devices.
Yep.
So in a lot of ways, there's a need for really thinking about co-designing, and that's what it's related to.
Yeah.
Algorithm hardware co-design that can potentially lead to not only improvement in latency, but also energy improvement. So it's really, for all these cases, I think there's a need to really think about, not just one aspect of the design, but really looking at the entire stack so that you can optimize it. Designing the algorithms so that it fits the right kind of hardware and the devices, or the other way around.
Well, thank you. It might be in the future we get more details on this project. I would like to thank you all now, and let's go for the lunch. Yes.
في technical devices by غلط. ورا هناك.
we need لو سمحتوا we need technical assistant please. We need a technical assistant. ما نبدأ غلط حقمت.
Sensors and MEMS, Electrical and Computer Engineering Professor, King Abdullah University of Science and Technology. Please welcome Professor Khalid Salama.
Okay, this is the first accident here. Assalamu alaikum, everyone. I'm very excited to be here with you, and I hope that I don't take too much of your time during this presentation. So we got delayed because I was the last one to send my slides. I sent them at 6 a.m. in the morning, and guess that meant that I'd be a little bit late. So today I'm going to be telling you about 3 PhD theses that just finished in my lab, the work of Dr. Abdullah Al-Mansouri, Dr. Mani Vijapu, and Dr. Tutku Baduk, and 2 of the master students and the PhDs that are continuing in the work right now. So when I was contacted by Xiao Hang, and he asked me to to talk about sensors and the current activities that we have at KAUST. So we started by looking into what we call conventional wearable sensors. And people who are working in this area are spending a lot of time. You look at the work by John Rogers and his colleagues. They do amazing science work. Basically, they are trying to actually integrate everything into a flexible substrate that is stretchable, that you can put on your hand, and you can do all these tattoos. However, if you look at these are more or less science right now. They are not going to be products because they are very fragile and they are very complicated to manufacture. So we looked into an idea of why don't we divide the problem of sensing systems into two components. One, which is the sensor itself. It's a passive component, and that shouldn't have any electronics associated with it. And then in a nearby to that sensor, we will have all your electronics, maybe wearable on your clothes, maybe integrated in your eyeglasses. And this way you can actually make it much, much easier to deal with the problem. So we looked into what we call magnetic skin. So magnetic skin is a membrane that you put on your hand, on your body, on your clothes, and that material actually has magnetic properties. The way we did it is that we incorporated magnetic micropowders with EcoFlex. And EcoFlex is a material that they use in movie theaters to make these monster type shapes that you see in Halloween movies. And then if you mix them both, depending on the concentrations that you mix, you can actually have a membrane or a material that has some magnetic properties. And the way we do it, we do 3D print mold, we cast it on it, then we planarize it, we put it inside a magnetic field, and then we release it, and you can even color it to give it all the shapes and the colors to match whatever technology you have. Of course, once you do that, you have to understand, are you really getting a magnetic material or not, and what are the properties of this material? So you plot here multiple parameters for the magnetic skin, and you can see that this material is extremely flexible. It has a 17 times lower Young's modular than PDMS, which is people believe that's very nicely flexible material. You can see the magnetization curves here. And one of the things that you have to worry about when you start working about these wearable things is that they are under a lot of stress. So you have to actually do mechanical stress to make sure that their properties change when you fold and unfold these types of materials. Now, once we start talking about a skin, this is something that's going to be on top of your skin. So you're going to be walking around, you're going to be sweating, and this will cause irritation and rash on your skin. So you have to start worrying about that problem. And the solution that we looked into is actually having holes laser etched inside the membrane. So what you have here is the different sizes of these holes and different concentration of these holes in a certain area. And of course, when you do that, what will happen is that the magnetic properties or the amount of magnet inside the membrane will get reduced, and you will lose some of the magnetic properties. So we're trying to do a trade-off, how much holes you can have so that you allow the sweat to perspire from your skin, and you can actually continue doing. And of course, once you start working on something in your body, you need to make sure, is it biocompatible or not? So you do some control experiments to grow cells and see if they can survive on this magnetic skin or not, or it's going to be toxic for you because you don't want someone to be wearing something that's toxic to his body. So once we achieve this magnetic skin, what are we going to be using it for? And first of all, I wanted to show you, so Abdullah is here, he's sitting in the audience. He's now a professor in Jeddah University, and it's very flexible. You can actually attach it to different points. You can move it left and right, and it's very easily adheres to your body. So the first example we looked into is monitoring your sleep patterns. Basically, we put one of these magnetic skin on top of your eyelid, and then we put the electronics on top of that. So what's happening here is that once your eye starts moving inside, it means that you are not sleeping, or you're actually not having very good sleep. So what happens is that the membrane starts moving or deforming and changes its magnetic properties. And if you have magnetic sensors in this piece of PCB, then you can actually monitor the change, and you can identify if the eye is moving and infer if the person is having bad dreams or is he actually sleeping or not. We then looked into another exciting project, which is actually helping people with quadriplegia. And the idea here is that we are actually going to outfit a wheelchair with all the electronics for receiver, and the receiver will get a signal from an eyeglasses that has all the sensors, and you put on your face three magnetic skins. So one of them is here, and one on the other side of your nose, and one in your chin. And what's happening here is that people with quadriplegia, they cannot use their hands, they cannot use their mouth, they cannot do many of the functionalities. So we figured out we can actually try to use the motion of your mouth, and I'll show it here in the next slides, so that you can actually send signals to the eyeglasses, and then the eyeglasses send signals to the wheelchair, and then the wheelchair can actually move around. So here is an example of the system. And what you see in the cartoon on top, basically, if you move, we came up with a code word. If you move your mouse to the left, if you move your mouse to the right, this will create a change in the magnetic properties of the skin that attach to your body, which is captured by the eyeglasses, and then the eyeglasses actually transmit it to the wheelchair, and the wheelchair moves. I realized in the last 2 days that we couldn't do movies, so I removed the movie and just put an image here. But you can see the same thing. One of the big things that you need to worry about is training people to use this technology. I mean, like, you have to actually have people, how long does it take them to train to get to master the code word, to move, to be able to move the chair forward, backward, left, right, and also to differentiate between someone speaking and someone moving. Because if you are starting to speak, your mouse moves, the magnetic skin will actually create a signal, and your chair will move. So you actually have to do some signal processing, and as fashionable now, machine learning, so in order to remove the unwanted signals, which is the speaking, from the actual commands you do for the chair. So this is one example of technologies that we developed. The next one is the gas sensors. This is one of the things that we have been involved heavily at CAUS since last 10 years. And I removed one slide by Manny, who did this work. He actually had 2 pictures for Taj Mahal before the pandemic and during the pandemic. And you couldn't see the Taj Mahal actually from 100 meters away. But then during the pandemic, it's actually visible from 1 kilometer away. It's a very nice demonstration. Another thing is Wuhan. You could see the satellite images before the lockdown and after the lockdown. It's extremely polluted, and then afterwards there is nothing. So it's a problem that we are producing. It's a problem that we have to monitor ourselves and we have to take care of. Not to mention that there are lots and lots of problems, health issues that actually come with pollution coming off for particle matters, as Murad talked in the morning, and from NOx. And there are lots of deaths, and the number 9 million people has been shown in the morning. So our technology that we use is that we build an indium gallium zinc oxide transistor. It's a thin film transistor as shown here. And one of the nicest things about indium is that it has the property to actually capture the molecules of NOx from the environment and provide a very strong bond. And traditionally, people would use ultraviolet in order to actually break this bond so that you can reset your device, or you can revive your device so that you can use it as a sensor. So the mode of operation is that first you reset your device, you make sure that there are no NOx or nitrogen dioxide molecules attached to your transistor, and then you put it, expose it to the environment. If there are NOx gases, they attach to your device, and then once they attach, they affect the current flowing in your device. So by measuring the current between the drain and the source, you can actually have an indication of how much gases are there. It's a very standard process of actually building this backgate transistor of an indium gallium zinc oxide. And the trick here is how to actually control the the amount of how much percentage of indium, how much percentage of gallium, how much zinc and oxide, playing with this recipe in order to get the best performance device you could have out there. Here are some of the plots of this transistor. This is just the top slide. This is a standard transistor, IV characteristics. It's a decent transistor. However, if you expose it to NOx, what you see is that the current changes and the threshold voltage of the transistors change. So this is a good indication that we can use that device as a sensor. So how can we do that? But before we go do that, just one brief comment about reviving it. Traditionally, people would revive it using UV LEDs, but we noticed that there is another peak in the blue light, and it's not as high as the one in the UV, but if you can use it for a longer period of time, you can revive the device. And having access to a blue LED is much, much cheaper and easier than having a UV LED to be integrated in your system for revival. So how can we do it? It's very simple. You put your transistor and you just put a resistor on top of it, and you can just follow the simple equation that the voltage is the VDD minus the current that is proportional to the gases in the environment multiplied by the resistance. You can see that we have a very nice linear range, and it can go all the way to 100 parts per billion. It's very repeatable. You can and we tested it over a long extended period of time. If you look into the selectivity, you can see that for 1 part per billion, you can have this large signal, while for 100 parts per billion, like 100 times more of these interfering gases, you could actually have a much lower signal. So it's actually a very selective device. We didn't stop at that. So typically, if you are working in the sensor arena, you stop and you declare victory. But we said, well, we have a transistor. Can't we actually build circuits and electronics with this transistor? And the answer is yes, if that's a good transistor. So the best way to do that is to prevent it from being a sensor. So we cover it with a parallel C layer, and this prevents any gases from going inside. Once you have that, then you have actually a very nice transistor. No matter how much NOx that actually it gets exposed, you get the same type of performance. So we went ahead and we built this very simple analog to digital converter. So basically you have your gas sensor on top, and you have one transistor, you change its voltage, that creates a current, and then you compare the currents, and you keep doing this sequentially, one by one, and you get bits, zeros and one, that are proportional. Are you higher or lower than the current that you are providing from your ballast transistors at the bottom? And if you follow that for different gas concentrations, you can see that we have a nice thermometer code at the bottom, the B1 to B5, depending on what was the gas supplied. So it's only 2 transistor, provides you a full system. You are going from gases in the environment to digital bits coming from your thing in only one similar, one technology, same process that you do. And you can here see the transfer characteristics of the system. One of my students didn't like this. He said that this is sequential. We want to do it parallel because I don't want to be waiting. So basically, instead of actually having 2 transistors on top of each other, you actually do current mirrors on the circuits shown here, and you actually provide different currents, and you do multiple comparisons. So in one shot, you can actually get 5 or 4 comparators, and you get the same performance and characteristics from that system. So we were lucky at KAUST that there was some company visiting us, and they were interested in actually speccing our system compared to technologies out there. So we gave them all the details, and they came up actually with this. They did this for us. They are the current systems that are out there in the industry, the sensitivity, the detection limit, range, and you can see that we are actually doing a very decent performance out of these devices that I showed you out there. However, I realized early on at KAUST that it's extremely important not to get people into your lab to see stuff. They want to see things and in the real environment. So we went ahead and we took it an extra step in my lab. So I have a very excellent engineer in my lab, and he developed this can that you could think of. It's a can of soda. It's exactly the same size of a can of soda with an LCD screen. It has actually inside a motor pump so that he can actually get the air from the environment. It has silica so that you can actually remove humidity, and you can pass it through our transistor. It has the LED control signal so that you can actually shine the LED so that you revive your device. And you can just carry it around, and you can actually measure the NOx that's in the environment. It caused us a lot of problems because we went to the behind one of the school buses at KAUST, and we can show that it's actually started peeping that this is actually exceeding the limits that you would have. So that tells you that our buses here in Saudi Arabia don't have very high standards when it deals with filtration. So that was a discovery. The last project that I want to share with you is actually moved. We got excited when we started building those prototypes and going to the field and testing them. It's not only just in the lab experiment. So we worked on electrochemical sensors. So the connections between all of this, I'm trained as a circuit designer, moved into building sensors as a complete system, but we don't really care much about what type of a sensor. We're looking into what type of a problem we're trying to solve. So as you all know, electrochemical sensing has been around for quite some time. All the lab experiments that are happening happens with bulky equipment. They are extremely good in sensitivity. They are actually suitable for basic research. However, they are time consuming. They are expensive. And there is a big need for actually moving into what we call in the field or on-site applications for these sensors. The best examples there, of course, diabetic patients. They have this device that can actually, a droplet of blood, that can tell you that glucose level in your blood, and the other one is the pregnancy test. And of course, everyone knows about the lateral flow for the COVID experiments. Everyone is having like few of these at home. So we decided that instead of having these big bulky things, why don't we build a version that is much, much smaller of this electrochemical station. They call it potentiostat, and we called it KAUST-stat. I mean, branding never hurts. So we built this system that allows us to do all the electrochemical experiment that anyone could think of. Linear switch voltmetry, cyclic voltmetry, differential pulse voltmetry, the list is out there. And we tried to make it as small as possible with off-the-shelf components that are out there. And we can actually have up to right now, the system we have is 8 channels. You can read 8 channels at a time. My student got excited that he bought this housing for a watch, and he put it inside, and he said that this is the next Apple Watch, and I'll call it KAUST Watch. In reality, what we actually deal with is a system that's attached to the cell phone, so it provides power and at the same time direct connectivity to your cell phone. And you do, basically what you have to do now is using this electrochemical station, which is miniaturized and it's extremely accurate, is actually to connect it to the sensor to do electrochemical sensing. And the sensors that we decided to work on is very fashionable these days. It's laser scribed graphene. It's very simple to actually build those 3 electrode systems. You get a polyamide sheet, you actually irradiate it with laser in the pattern that you like, and you get the 3 electrode system that typically are used for screen printed electrodes or the other types of gold screen printed electrodes as well. And you can actually immobilize on these electrodes the capture probe. So every material, there is a capture probe that can capture it. So if you are looking, for example, for a center type of an antigen, you know what type of antibody you attach to your sensor. So when you flow your sample on it, what will happen is that it will capture on it and it will affect the current flowing into your system. And if you measure that current, you actually get an indication how many of these you captured, which is an indication what is the concentration of the environment of this material. In this example, we looked for the spike proteins that are actually associated with COVID. And here are some experiments just to show you the sensitivity, the diversity of our results, and also the selectivity against different types of proteins that are out there. So it worked, and we were very excited, very happy about this. However, during Corona, we were on complete lockdown at KAUST. So one of my students, Tutku, she actually asked me if she can go to Turkey, because in Turkey, she could actually go into one of our collaborators' lab because it's fully open. So we said, yes, of course. And luckily, at the same time, they were also working on Corona, but they had access to clinical trials. They were actually access to the hospital. So we did actually our first clinical trial with 23 patients, where we are comparing the golden standard, which is the real-time PCR, versus our system. And you can see that complete match between the positives and the negatives, compared to the FDA-approved ELISA, the fast rapid techniques. And you could have that they have actually errors because they have false positives and false negatives that shouldn't be out there. So this was actually a very exciting project that actually got involved in because it worked in the hospital directly with real patient samples. But this was based on blood serum. So we looked into but people use actually nasal swabs in order to actually detect these proteins. So we started looking into 2 problems. How can we work with nasal swabs, but at the same time, can we identify which strain of actually COVID is there? Is it the South African version or is it the UK version? Because it depends on 2 different types of proteins. And can we actually try to do detection of both proteins at the same time? The answer is yes. It's simple, but it comes with a problem. You are actually detecting 2 at the same time, so there is a lot of interference, and it becomes like people who are in communication understand this MIMO. So there are actually, you're sending multiple symbols, and they overlap with each other. So you have to do some denoising, and the popular way of denoising right now, again, is using simple machine learning techniques. And basically, we build a neural network. And the good thing is that once you have an acquisition system that we built, it has actually a microprocessor on it as well. So we can actually do this directly on the chip, do the whole algorithm, and it takes a very, less than 1 minute to actually calculate the results. I identify, is this negative sample, or is this the UK positive, or is it South Africa positive? So this was also another example of how can we merge computing with sensing, with communication, all in one system with real experiment. And this, again, was a clinical trial with 43, I think it's in the previous slides, 43 patients, and we have another one going with 50 patients. So with that, I just want to thank you so much for giving me the time to highlight the work of many of my students here at KAUST that did amazing work. Again, thanks to Abdullah, to Tutku, to Mani, to Saravanan, and to Jose. Here are the ones who contributed to the work in this slide. Thank you so much.
Thank you, Professor Khalid. Director of the National Center For Electronics and Defense System at CAXT, please welcome Dr. Majid Al-Ghamdi.
Assalamu alaikum wa rahmatullahi wa barakatuh. Hello and welcome everybody to this forum. Before to begin, I would like actually to thank CAX and CAUS to work collaboratively to arrange this event and to actually meet the top leaders in the fields to inspire innovation into our work. Today, where is my slides? Okay, good. So today I'm going actually to talk about inertial MEMS sensors and show you our research efforts and latest findings on this topic. So here is my outline. So I'm going to actually give you a brief about our center and what we do, and then I will move to talk about why are we going to MEMS technology, and then I will move to highlight our work and our achievement at the inertial MEMS sensor that actually developed here at CAXT. So first of all, let me give you a brief about our center. So the National Center for Electronics and Defense System is one of 5 specialized centers at the Communication and Information Technology Research Institute. Our main focus is to develop prototypes in the fields of electronics and defense system in order actually to enrich R&D and strengthen R&D ecosystem in Saudi Arabia, and that leads actually to support Vision 2030. Our center has 4 main research groups focusing on electronics, starting from the component level all the way to the systems level. So in the component level, we focus on designing MEMS and the ASIC, which is actually electronic circuit that translate the mechanical motion of into electronic signal. And also we have a team dedicated to integrate these sensors together and connecting them to the internet or any communication network to come up with an IoT system. Then we have a research group focusing on radar and electronics warfare, and also telecommunication system and information security system. Currently, our staff consists of more than 100 researchers holding a PhD from the top universities and master's and PhD. And and these are actually the statistics of our researchers and their specialty. We have published actually more than 100 scientific journals and filing more than 100 patents during the 10 years. And we have 4 specialized labs dedicating to accomplish all the center activities in all these main research areas. So now let's move and talk a bit technically and about the subject of this talk. So we're going to talk about MEMS. What's MEMS? So MEMS actually stands for electromechanical systems. It's a transducers that are made of semiconductor, usually silicon. It's fabricated using microfabrication process in order to create, to make sensors and actuators. As actually from the name of the MEMS, actually it's combined the electrical and mechanical capabilities in one device as small as a few of micrometers to sub of millimeters. It confers actually the physical quantity change as a velocity or temperature and to electrical signal. And the MEMS actually has an advantages to be in a wide range of application, and that's actually due to miniaturized size, efficient power consumption, and low cost in operation and fabrication. So here is actually one of our micro devices that actually have been recently fabricated. It actually consists of 4 inertial sensors, and this is the fabrication process of this device. So these actually these advantages of MEMS sensors allow it to actually to be in a wide range and exponentially growing. So as we can see from this actually figure, it shows the evolution of MEMS sensors starting from 90s at the automotive industry and going to micro devices and adding some intelligence to it toward the IoT, autonomous, and robotic system industry. This is a market study that has been actually published in 2021. It shows, as we can see, it shows the market value of MEMS sensors accounts for $12.1 billion on 2020, and actually it's expected to expand to reach $18.2 billion on 2026. And also, as we can see, the MEMS market applications rely heavily on consumer application, which actually accounts for $7.13 billion in 2020 and expected to expand to reach $11.27 billion. 25% from the MEMS total market is dominated by inertial sensors. The biggest market players of MEMS inertial sensors are located in US and Europe and Middle East, with a market value of $2.24 billion in US and $0.65 billion in Europe and Middle East. The Middle East now, it's actually growing and expanding in technology. And here in Saudi Arabia, we actually rapidly growing and expanding in technology and innovation. So in the same context, our center has been transferring the microsystems, especially inertial sensors, toward Saudi Arabia since 2009. Our main objective is to localize and develop inertial sensors as accelerometer, gyroscope, inertial measurement unit, and inertial navigation system that actually can be deployed in a wide range of applications, such as military, industry, or industrial application, or emerging technology. These inertial sensors, actually, the impact of developing this inertial sensor can be actually increased and localized and transfer know-how to Saudi Arabia, and also to building capabilities, in addition to enrich local market. So the supply chain of the inertial sensor consists initially of front end, where we develop the MEMS and the ASIC and integrating them in one chip, going to the back end, where we package the sensor and the ASIC together, and then going to the second level of packaging by having a module or transducers and fitting them in application to perform actually its performance in a pilot projects. So here in CACS, we are heavily engaged on the front end, and now we are planning to explore all other elements to have the complete value chain of inertial sensors. So one of our senior visions is to develop INS system. So as I mentioned in the previous slide, we focused on the front end. So we started with designing an ASIC and then building capabilities at this level, and then moving forward to building capabilities on MEMS, integrating them together to go to the inertial measurement unit. So we are at this level right now, and we are moving forward toward our vision to have an inertial navigation system. We are more than happy actually to collaborate on all these levels of having an INS. So now let's talk about our previous achievements. So in 2009, we have started transferring this technology with our strategic partner, Cyber Systems. So at that time, we were working actually to develop three types of accelerometers targeting 3N application. So we went through all the development process, starting from designing and obtaining numerical and finite element model, and analyzing the static and dynamic analysis of it, going to participating in fabrication. And here in this project, we have fabricated actually in Paris at the EZA clean room, and then we have characterized it and tested in our lab. So these accelerometers were targeted actually in application of vibrating monitoring as the one on the top right, and the second one for tilting measurement, and the third one for airbag systems. Also, the team actually was designed an ASIC, which is application-specific integrated circuit for these accelerometers to translate the mechanical motion of the MEMS into electrical signal. So this is a demo that has been actually recorded under a probe station inside the clean room, just to make sure the releasing process had been successfully achieved. And then we increased actually the complexity and trying to design another type of inertial sensors, which is gyroscope. So the gyroscope is used to measure the angular velocity of an object. So here we have developed three type of gyroscopes, and we went through all the project phases as explained previously in the previous project. We went through the design phase and obtaining the numerical and finite element, and then participating in fabricating these sensors and then characterize it and test it. This is actually gyroscope targeted inertial platform stabilization for motion sensors in smart devices and optical image stabilization. And actually, this gyroscope and the previous accelerometers were as a technology transfer, so we focused to building capabilities and transferring this technology to Saudi Arabia. Then the team also was developed a single-axis ASIC, as I mentioned, to actually translate the mechanical motion into electrical signal. And this ASIC technology was implemented in the technology of 180 nanometer. So this is also a demo of the gyroscope that has been recorded inside the clean room. We excited with the different signal frequencies in order to check the releasing process. And this was actually successfully released. And then we actually targeted to have higher spec and higher performance of gyroscope. So we used a different type of gyroscope that's called tuning fork gyroscope, where we have a pair of masses instead of one. So I'm not sure why my slides looks like this, but anyway. So the first one, the first one in the left, it looks actually small in size, and we achieved a better performance compared to the previous one, and achieved a better decoupling efficiency, specifically mechanical decoupling efficiency, in order compared to the previous one. And then at that time, we also focused to have high decoupling, mechanical and electrical, high decoupling efficiency, and we come up with this bulky design. I know it's bulky, but actually because the Coriolis force is directly proportional to the mass, but actually we achieved really high decoupling efficiency. We are working now to file a patent on this design and publishing significant results. And after we gained lots of experience during the previous projects, we were also targeting to moving up to the INS, So we developed a 6 degree of freedom inertial measurement unit, three-axis gyroscope integrated with the 3-axis accelerometers in order to measure the linear acceleration and the angular rate of an object. So at this project, we went through 2 tracks. The first track, just to focus on develop monotonically 3-axis gyroscopes. And the advantages of developing this project is to overcome on the alignment issues between the 3 axes. And at this track, we went through the development cycle of designing and fabricating and testing this gyroscope. So this is the monolithic 3-axis gyroscope. And in the second track, we capitalized on one of our best performance single-axis gyroscope, and we took 3 of them and we aligned them vertically, as we can see in the middle bottom one. So, and then we integrated with the off-the-shelf 3-axis accelerometers in order to have a 6 degree of freedom IMU. And also, we have developed a single-chip 3-axis ASIC to translate the mechanical motion of the monolithic 3-axis gyroscope. And also, we have also developed as the ASIC that we have developed in the previous project, we have a single axis to actually translate the mechanical motion on the second track. So here is actually the ASIC design. And as we can see also, the monolithic 3-axis MEMS, and the small one, it's actually the 3-axis ASIC. So this is actually the Allen variance testing results of one of our gyroscopes. So the Allen variance is used, actually, it's a standard method to characterize the intrinsic noise of a gyroscope over averaging runtime. So here, from this figure, we obtain two most important parameters, which are the bias instability, which describe the bias over averaging runtime. And we also obtaining the angular random walk, which describe the white noise into your sense signal output. So we found the bias instability 5.5 degree per hour at a bandwidth of 300 hertz. And the angular random walk was found 200 meter degree per square root hertz. We have published actually this work recently, so you can go and check all the experimental results that have been done extensively in our lab. So here is the 6 degree of freedom IMU, and we can see also the ASIC and the MEMS chip before packaging them and after we package them. Also, we can see here the two experimental results of other Allen variance. These results we haven't published it yet. We achieved 1.7 degree per hour for the bias stability. And the angular random walk we achieved 69.7 millidegree per square root hertz. And also on another design, we achieved 1.6 degree per hour, where the angular random walk 64 millidegree per square root hertz. Just actually for demonstration purposes, we put in our IMU on an airplane just to demonstrate the operational principle of gyroscope. And yeah, so this is the reason of recording this video and show how it moves and how it's actually detect or measure the subjected rotational. Here actually is our actually specialized lab in our center. So we have an electronics and radar and electronic warfare labs, and also for telecommunication and information security lab. We are more than happy to collaborate in these center activities. And Feynman was right, there is plenty of room at the bottom. Thank you so much.
Thank you, Dr. Majid. Assistant Professor, Electronic and Computer Engineering at King Abdullah University, please welcome Dr. Nazik Al-Atab.
Hello, everyone. So I'm Nazik Al-Atab, an assistant professor of electrical and computer engineering at KAUST. I have joined KAUST around 9 months ago. So today I will be presenting some of my past research experience, and also I will be explaining the research that we're currently focusing on in my lab at KAUST. So currently, we are constantly moving towards a more and more digitized world where interconnected smart devices interact with the physical world and communicate seamlessly over the internet. This digital transformation is taking place thanks to several exciting technologies, such as the Internet of Things, artificial intelligence, augmented reality, among others, which are bringing numerous benefits to our lives throughout different fields, such as transportation, healthcare, agriculture, among others. Now, if we take a closer look at any of these smart devices, we can see that they include several key components. For example, if we take the example of a smartwatch, an Apple Watch, and we disassemble it, we can see that it includes several key components, which are the communication unit, sensors, processor, memory, and power units. And we can see that as the memory and processor units have improved over time, we were able to include additional sensors, communication, all of which require higher capacity storage, in addition to the ability to transfer the data quickly and reliably. Therefore, the continuous progression of memory devices has been a key technology enabler. Future exciting technologies require memory devices to be fast and reliable, high density, low cost, and low power. But what is the current state of the art for memory devices? So memory devices can be divided into two main categories, non-volatile and volatile, where volatility means that the data would be lost if the power is turned off. So if you look at the NAND flash, which is currently being used in more than 99% of the applications, according to the International Roadmap of Devices and Systems, we can see that it is at a low cost, but it provides a slow access time. On the other hand, the DRAM, which is volatile, provides a much faster access time, but at the expense of a higher cost. Futuristic applications require being able to combine between the benefits of these two memory devices, especially if we think about AI and autonomous cars, where the data needs to be stored in memory devices in real time, and also the processor needs to be accessing the data stored in the memory devices really fast to analyze them and make future decisions. Therefore, researchers have worked on developing emerging memory devices which operate using different operation mechanisms, such as magnetic RAM, ferroelectric RAM, phase change RAM, and resistive RAM. And while these emerging memory technologies are able to show faster and lower power consumption compared to flash memory devices, however, there are several bottlenecks that they need to overcome, such as having lower density, being more expensive, and showing reliability concerns. Therefore, the main requirements for future memory devices remain being able to combine between non-volatility, high speed, high density, low power, and low cost. So in terms of flash memory devices in specific, the International Roadmap of Devices and Systems specifies two main solutions to be able to continue scaling them down. So the first one is to stack these flash memory devices in 3D, and this is already commercialized, so it's already there at the industry level. The other solution is to use innovative material combinations and architectures. So this has been the focus of my previous research, where I have worked on the fabrication and design of nanomaterials-based flash memory devices in order to enhance their performance in terms of lowering their operating voltage, enhancing their endurance, retention characteristics, and speed. So we worked on the simulation initially of these devices to understand their physics, how the different materials affect the properties of the device, the performance of the device. Then we worked on the actual fabrication and characterization to explain the observed behavior. And some of the nanomaterials that were studied include silicon nanoparticles, indium nitride, zinc oxide nanoparticles, and graphene nanoplatelets. And using a double layer of tunnel oxides and graphene nanoplatelets trash wrapping layer, we were able to show the lowest operating voltage in flash memory and the fastest program erase speed. Now here I would like to note that these nanomaterials were fabricated separately, and then they were coated onto the memory device using a specific coating technique, such as spin coating or drop casting, while the remaining active layers of the memory device were fabricated using a specific tool called the atomic layer deposition tool. Therefore, I have also worked on the growth of these nanomaterials using the ALD tool so that we can grow all the active layers of the memory device in a single step, in a single tool, which means faster fabrication, less contamination, and therefore better reproducibility and faster potential tech transfer. So by playing with the growth conditions in the atomic layer deposition tool, and by also modifying the substrate termination, we can get nano-islands instead of a continuous thin film in ALD. So here you can see that we were able to show zirconia and zinc oxide nano-islands. We have shown their unique properties compared to the bulk thin film. And then we have shown the first demonstration of potential application of these nano-islands grown using ALD in memory and solar cells. Okay, so far I have been talking about memory devices and their importance. However, a memory device is not very useful on its own. It has to be integrated into a complete system to be useful. If we consider the existing integration and packaging technologies, we can see that usually they have trade-offs in terms of high performance, low cost, reduced area, and multifunctionality. Therefore, in order to overcome these limitations, in specific in IoT applications, I have worked on, not sure, okay. So I have worked on the design of a new integration and packaging technology that we call a multi-dimensional integrated circuit, mainly targeting IoT applications. So here you can see the cubic system where on each side of this system we have integrated thin film-based components on both sides of the wafer, and they are interconnected using through substrate vias, while the side-to-side devices are interconnected using side interlocks in a puzzle-like fashion. So each side of this cubic system can be based on a different material in order to get a high-performance system. Also, each side can be fabricated separately and tested separately, which means lower cost because we do not need to have complicated lithography masks, and a higher yield because each side can be tested separately before joining them into a complete cubic system. And we have shown the application of this system in food and water quality in fish farming ponds, which is aligned with the Saudi Arabia 2030 vision, where $3.5 billion are actually being invested in aquaculture. So aquaculture provides more than 50% of the seafood that we consume globally. However, the pollution is known to be the main reason for the fish death worldwide. So being able to monitor the water quality in real time is really important. And if you look at the existing solutions in the market, you can see that they are either bulky and expensive and they require installation by experts, or they are small and lightweight, but they can measure only 1 or 2 water quality parameters at a time, so it will be a time-consuming solution for the farmer. So using this cubic system, which integrates thin film-based sensors, a microprocessor to analyze the data, a solar cell to harvest energy, and a BLE unit to transmit the data wirelessly. And by encapsulating this system using PDMS, which is eco-friendly, we can actually throw this system into the water, and it will autonomously rotate and adjust its position and start collecting the data about the water quality and sending them in real time to the farmer. Okay. So in order to make a system self-powered and standalone, we need to integrate energy harvesters. And solar cells are one of the most promising energy harvesters. More specifically, if we think about futuristic applications such as wearables, robotics, drones, we can see that such applications require the integration of flexible and stretchable energy harvesters. So in terms of flexible and stretchable solar cells, we can either use organic materials, which are mostly inherently flexible and some are stretchable, but they usually show lower efficiency in solar cells, in addition to having reliability issues. While if we use inorganic materials, they usually show higher efficiencies, but they are brittle and rigid. So in order to make them flexible, researchers have focused on thinning down the material and transferring it onto a flexible substrate, or directly growing these solar cell materials on top of a flexible substrate. And both of these approaches usually result in lower efficiencies compared to the rigid counterpart. So in order to overcome this limitation, I have also worked on the design and development of a fabrication process flow, which allows us to convert a rigid, commercial-grade, large-scale, inorganic silicon-based solar cell into its ultra-flexible and ultra-stretchable version using two simple steps, CO2 laser patterning and deep reactive ion etching. And you can see that the different corrugation patterns result in different flexing and stretching capabilities. So using this technique, we're able to show world record flexibility and world record stretchability. Also, these solar cells can be stretched not only in plane, but also out of plane, which can be useful for different applications in robotics. We have also shown the ability to wrap these flexible solar cells into a 3D architecture, a spherical solar cell, which can harvest light three-dimensionally from all directions. We have also applied these flexible solar cells on drones, which was a project funded by Lockheed Martin. And we have shown the extension of the flight time of drones using these flexible solar cells. Okay, so currently in my lab, we're focusing on the design and development of smart memory devices. So if you remember at the beginning of this talk, I mentioned that we need to continue improving the performance of memory devices. And this has been traditionally made by scaling down flash memory devices, but this cannot be pursued indefinitely due to physics limitations. So researchers are currently looking into alternative approaches to make faster and more real-time data analysis without having to scale down these memory devices. And one solution is in-memory computing that Professor Roy mentioned at the beginning of this, in the morning. So complementary to this technology, we are working on in-memory sensing, where we would like to combine between the roles of memory and a sensor in a single device. So if you think about an IoT system, the data usually needs to go through from a sensor through an energy and time-consuming ADC unit to the memory processor, among other components. So what we would like to do is we would like to get rid of the ADC and combine between the memory and sensor into a single device, which is capable of in-memory sensing. Such a device that we call MEMSER, when exposed to an external stimulus, such as pressure, for example, would be able to store the pressure intensity within it, while a light MEMSER, when exposed to light intensity, would be able to store the light intensity within it. So in such a device, since we are combining between the roles of two devices in a single device, we would be able to achieve faster response, lower area, and ideally lower power consumption. We are working on the design and development of these in-memory sensors based on flash memory devices architectures, since they are already being used in more than 99% of the applications, and it's a mature technology. But by integrating stimulus-sensitive materials, such as 2D materials and semiconductor quantum dots, we can achieve the sensing capability. And similar to a traditional flash memory, which can store multiple bits, the in-memory sensor will also be able to store multiple bits, and the different states will be representing the different intensities of the external stimulus. Finally, I would like to so the in-memory sensing device can be complementing the in-memory processing technology to achieve an even more compact system with faster and more real-time data analysis. And we believe that such a device would be most promising in applications which require fast and real-time data analysis, especially data that is being acquired from sensors, such as autonomous cars, Internet of Things, augmented reality, among others. So this is related to smart memory devices, but we're also working on the simulation and design of memory devices with the traditional role of storing data. And we're trying to improve their performance in terms of lowering their operating voltage, enhancing their endurance and retention characteristics and speed using advanced architectures such as nanosheet FET-based memory devices and wavy channel nanosheet FET-based memory devices. With that, I would like to thank you all for your attention.
Thank you, Dr. Nazik. Associate Professor of Bioscience Current at King Abdullah University, Please welcome Dr. Shahika Inal.
All right. Hi, everyone. Thank you so much for the organizers, colleagues from CACST and KAUST for their kind invitation, as well as making such a great program and bringing all of us together. I'm very excited to give this talk today, and I'm also very surprised to see a green screen of my black background slides. I do really hope that the slides are at a good condition. All right, let's see. And I'm an associate professor of bioengineering, and I'm coming to this community more from the biology end and the chemistry end. So the field that we are working on is called organic bioelectronics, and this is what I'm going to introduce you today. So bioelectronics is a field that couples the roles of biology with electronics in order to develop devices that can either detect diseases or treat them. And you can think about these devices as a full spectrum. On one hand, you have these diagnostic devices, electronics or semiconductors used for disease detection, like glucose sensors or a coronavirus sensor Khalid Salama has introduced. Or similar electronic devices can be used for very unconventional therapy purposes, like electrical stimulators that can be implanted and then repair the malfunctioning part of a particular neuron or a neural network. However, making such devices, electronic devices for biology is very challenging because, as you can imagine, the roles of biology and electronics are very different from one apart. In biology, the tissue is soft and it's in water, whereas the conventional electronics and semiconductors, they are rigid and they do not like water. And we need to spend a lot of fabrication efforts to make them have mechanical properties that match that of the tissue. There are also differences related to the way how signals are transmitted. Biology uses ionic signals for signal transmission. Cells, they do communicate with one another using ionic charges, whereas conventional electronics have electrons in a solid lattice. So there's the currency of biology and electronics are very different. And a third difference that I can say is about the time scale of events. In biology, everything is dynamic. We are born small, we grow, so everything evolves over time, whereas conventional electronics are static systems. Now, because I'm coming from a material science perspective to this field, the way how I bridge electronics to biology is through the use of materials that are more bio-friendly. And there's one particular type of material I think that fits the job very well, and these are called organic semiconductors. They provide a new toolbox for interfacing with biology because of the unique set of properties that they have. So for those of you who are not familiar with such molecules, you can see on the right-hand side some aromatic structures. So these can be either small molecules, all carbon, nitrogen, or oxygen-based. So everything that is found in our body, they carry the same chemical structure. Or you can have these polymeric chains, long chains, polymers, where charges, both ionic and electronic charges, can transport along. So therefore, we are using these type of films to make electronic devices. And besides those properties, they are cell-friendly, they have improved mechanical compliance. When you make a film and put them in water, they like taking up that water, so they become much softer, therefore more mechanically compliant with tissue, without you needing to do anything to change in their properties. Their processing is not vacuum-based, so you can just make a solution, even in water, and then just cast them on a surface, and then you have an electronic film, which is quite useful when we want to make different types of structures. And most importantly, for me, from the eyes of a polymer chemist, I can say that they're also quite diverse. You can change the chemistry for a particular application that you're going for. You don't need to do too much post-processing methods. You can have a material already that has the property that you're looking for. And you can generate charges. I think that was a topic that was discussed yesterday. By shining light, you can generate excited species. By applying voltage in an electrolyte, you can introduce ionic charges, which then couple with electronic charges, so you can, again, make an insulating polymer a conducting one. So they have redox activity, as we call it. And again, I'm repeating that one. They do show mixed conductivity. In addition to electronic charges, they can transport ionic charges, which is the currency of biology. And we use especially this mixed conduction as a way to communicate with biological systems when we make electronics based on these organic semiconductors. Now, this is what my lab at KAUST is doing, the lab of organic bioelectronics. We do work a lot, mostly on the charge transport properties of these conjugate polymer films. We develop various techniques to look at these new types of semiconductors, how they transport charge, how they act in water under different voltages. And then when we find some interesting candidates, then they do have very interesting properties for a lot of types of devices, including memory, including LEDs, including photovoltaics. We then go ahead and design bioelectronic devices, and our current focus is more on sensors. We make devices that can detect neural activity, ion channels that all the cells are carrying, those ionic signals that are very important for us. We do look at put actual cells, like living cells, on top of these devices and try to understand their behavior without needing to go to human tissue level. And we do also do detection of certain disease biomarkers, such as proteins, nucleic acids, and metabolites. So I know that I don't have much time, and I know that the audience has quite broad interest and background. That's why I chose a couple of technologies that we are developing and we have developed in the lab, and give you a glimpse of this field. So what do? We love using transistors that use these organic semiconductors in their channels. And relying on this mixed conductivity that they perform, we are making sensors for various purposes and with different operation principles. For example, we do make organic transistors on flexible substrates. We typically use parylene as a substrate and use these transistors to detect signals from mostly cortical neurons with efficiency that cannot be reached by conventional electronic devices or either electrodes or transistors. In another application, we put cellular layers on top of these transistor channels and then look at how, for instance, drugs affect the cells, because the transistor output is directly correlational to the well-being of these cellular layers, so that we use these micron-scale transistor platforms to measure the toxicity of certain chemicals. In another application, either by functionalizing the gate electrode of the transistor or directly the channel, the organic material, by biorecognition units, we are detecting analytes with performance, again, that exceeds the state of the art, and I'm going to show you what that means. Now let's look at the first application that I want to talk about, how we are using organic electrochemical transistors, these transistors that are based on these mixed conductors that I mentioned, for virus detection. And that became quite an important topic, as I don't need to motivate you, I guess, for the importance of detecting pathogens any longer. Before Corona, I had to, but now I do not spend time for that. So this is a typical transistor that we produce at KAUST in our core labs in the nanofabrication facility. You can maybe see 6 identical channels, organic channels, and they're directly interfacing a liquid, so they're quite air and liquid stable. You don't need a special environment for their operation. But the transistor alone like this is just an amplifier and a transducer. It's nothing selective to anything. That's where our biochemistry knowledge comes in play, because we do work with protein chemistry groups to functionalize solid gate electrode surfaces with certain recognition units. And for this particular application, we use very small recognition units that are called nanobodies, which are sensitive to the protein that is around the virus. So once that protein binds to the nanobody that is on the gate electrode of the sensor, we do detect signals from the channel whose current changes as a function of the virus concentration in the liquid that we are looking for. And the interesting thing, I think, about these sensors is that, so they're quite fast. The detection happens within 10 minutes. They're very sensitive. I'm going to show you how. They're quite selective because of the specificity of that nanobody layer that we use. They don't use any enzymes. There are no like additional reagents that you need to have. And they're mostly reusable, meaning that you can take the base of the transistor and use it multiple times, and all you need to change is the gate component, which is much cheaper to produce. So you can have multiple sensors for measurements, and as well as you can have sensors for different types of viruses as well by using the same transistor base. So the operation of these sensors are very simple. That's the gate electrode that we incubate with the patient sample for about 10 minutes. Afterwards, we are rinsing the gate electrode with a buffer solution, and then flip it, and then interface that transistor base, and just start basically taking signals from those 6 different channels and get a common output signal. And we did a lot of studies. I'm just showing you the end result. These are results that we got from King Faisal Specialist Hospital and Research Center in Riyadh. At the time, that was the only facility that welcomed us to validate our devices. So a team from KAUST went to Riyadh and started measuring these samples, these devices with patient samples. And as you can see, the nasal swabs that are coming from the patients, as well as the saliva samples, the raw saliva without having any processing procedure, can be used with these devices, and they have accuracy as good as the RT-PCR, with sensitivity reaching to RT-PCR, which is quite new for these type of antigen sensors. So as you know, the biggest problem with antigen sensors is that they can't detect people with low infection levels, because their saliva or their nasal swabs don't have enough virus for the low sensitive devices that they have. But these transistors work in a way that they can reach to attomolar concentrations, that is about single molecule concentrations of the protein that they can detect. And they do this with the speed of lateral flow immunoassays. And currently, thanks to the funding that we got from the translation office that's at KAUST, we are working with third-party companies to make take these devices from the lab and have a universal prototype and make them market ready. In another application, we are focusing on another protein type, but these proteins this time are found in blood. So I don't know if you're familiar with Alzheimer's disease. In an Alzheimer's disease patient brain, there are plaques, agglomerates of a particular protein that's called amyloid beta. And once these amyloid beta proteins start accumulating in between neurons, they inhibit their communication. Now, there are some studies that are showing us that these amyloid beta aggregates can be also found in the blood, which is offering a way to diagnose Alzheimer's disease early enough before the onset of even the signals. And when we see that, we went ahead and started thinking about how we can make a sensor to detect such aggregates from the blood. And for this work, we decided not to functionalize any part of the transistor, but this time to work on an interlayer, a porous membrane, an isoporous membrane that is normally used for water filtration. And that was a membrane that was produced like very cheaply in the in Suzanne Nunes group in the Water Desalination Center at KAUST. Oh, 1 minute, amazing. And we functionalize these membranes with a material that is sensitive to these amyloid beta proteins, and integrated it with our transistors, and as well as a microfluidic channel to allow for sample introduction much easier. And by using N-type organic semiconductors, we started getting signals that are very sensitive for the detection of such aggregates. I'm just going to quickly pass this because this is just another sensor. If you're interested, you can take a look at those and how we use, again, N-type polymeric conductors for metabolite detection at nanomolar concentrations, as well as how we use these polymers as the contact of an all-polymer-based fuel cell, which basically turns metabolic power into a voltage, which are then used to power the sensors that we use. And a final application that I want to share with you are these organic microelectrode and transistor arrays that we produced in the lab. And these devices we are typically using to, again, either culture cells directly on top, and cells really like these surfaces because of those properties that I mentioned to you in the beginning. And for instance, these are some breast cancer cells that are growing on the transistor channel. Why do we do this? Because we want to see, for instance, how healthy cells turn tumor-like under certain conditions, but we don't want to do any microscopy measurements, but we want to do continuous electrical monitoring, which these type of transistors allow us to do within quite a long time. And the same transistors you can also use with cortical neurons and now start stimulating these neurons with electrical signals with the same devices, and then use the same devices also to detect signals from them. So all I want to say, semiconductors, I think, are a major player in the future of healthcare. We are going to see in the next 20 to 30 years so many of them dominating healthcare in the area of sensors, in the area of drug delivery, electrical stimulation, e-skin wearables. They're already in our lives, but we are going to see them much more. So biomedical engineering is a growing, booming field, and electronics, and especially semiconductors, and more importantly, customized materials are very important for this field. Well, thank you very much, everyone who listened to me, as well as all the group members and several collaborators we have within the kingdom at KAUST, as well as abroad. Thank you.
Thank you, Dr. Inal. Assistant Professor at KAUST, please welcome Dr. Radwan Noor.
Thank you all for attending my talk, and I would like to thank also the organizers from KAUST and KAUST for making this really nice event. So our talk today is about microfabricated atomic sensors. It's quite different than what we've been hearing for the past 2 days. I will introduce these sensors really quickly and highlight on the role of MEMS fabrication techniques in miniaturizing these sensors. So when we say atomic sensors, some of us, or like the majority of us, know that the atomic clock is used for timekeeping, and the definition of the SI unit second is done with cesium atom since the 1960s. And we can see here the state-of-the-art atomic clock, which is claimed to have an error less than 1 second in more than 100 billion years. Billion years with a B. This is due to the fact that atoms are identical and perfect, unlike any other devices or MEMS we fabricate in labs. So what other types of sensors or atomic sensors do exist? We can see here 2 of the lab setups for atomic magnetometers and atomic gyroscopes. These sensors use a cloud of atoms in special conditions to make a precise measurement. One very clear, everyone can notice that these sensors are bulky. These like huge, they take rooms, and they only exist in labs. But they have a quite impressive performance. And you can see like all the engineers and researchers have started asking themselves, is it possible to take these from lab setups down to the field and miniaturize them? And this is what we'll be talking about today. Let's first talk about how do atoms sense. Basically, I don't want to get into the physics or the math. For everyone is tired. This is like the last session for this forum. We need to prepare atoms, and then we excite these atoms so they are in the most sensitive state, and then we can read whatever property we are interested in, either magnetic field or gyroscopic motion or whatever. Before we talk about the miniaturization. Let's take a quick look on the anatomy or the basic building blocks of these sensors. First, we need, as I said before, these atoms in gas phase. So they need an atomic cell that can hold all of these atoms in a confined location. We need lasers and light sources to be able to polarize them and increase their energy levels, as well as optics and detectors to be able to control the polarization and the reflection of the lights. We need magnetic field coils and also good electronics to be able to control and the signals and the readout of these signals. And some of these sensors require shielding because these cells have the magnetic field inside is almost 6 orders of magnitude to 9 orders of magnitude smaller than the field that we of the Earth field that we can measure with compasses and magnetic sensors. So there are 2 key technologies that contributed to the miniaturization of atomic sensors. Before I talk about them, let's take a look at the typical atomic cell. These cells are made of quartz or glass, and they are a few centimeters in size. And the first technology that enabled this is the microfabrication techniques or the MEMS fabrication techniques, where researchers were able to miniaturize them and put them on a wafer level by batch fabricating them. Of course, when you go smaller, problems start to coming up with all this big space in the typical cells. And then when we go smaller, special conditions need to be taken care of when we talk about the gas composition. We can see here some of the researchers that were able to miniaturize them, and we can see in the middle in our lab we were able to fabricate micro bubbles or micro glass blown cells on a wafer level that on the order of a few millimeters. The second technology that enabled this miniaturization is the availability of light sources at the wavelength of the alkali metals, which we use inside our cells, namely the rubidium and cesium. And of these light sources, the VCSELs were the largest contributor to this miniaturization trend because of their low power and low cost. Of course, these atomic sensors required very narrow line width and high stability to be able to manufacture. Other components were miniaturized using microfabrication, like the coils. We can see here the tabletop coils, and people were able to make it on a wafer. Heaters, optics, like lenses, and etc. And of course, we cannot forget about the evolution that happened in the electronics since the 1960s until today. So I will be giving 3 examples of atomic sensors: the atomic clocks, the atomic magnetometer, and the atomic gyro. I will try not to get into too many details of how these work, and then I will give some examples of each of these sensors. We see here the typical schematic of the atomic clock with all the components that we have talked about before. So how do these work? First, we prepare the atom by shining the light, and then we excite the atom by applying an external RF signal to modulate the light. So, and then when we excite the atom to the higher energy state, the emitted light from this atom are used to stabilize the crystal oscillator that we use as a reference. So, and then we have a very sharp resonance called the coherent population trapping resonance, and these are what researchers have used to stabilize the conventional resonators like crystal and MEMS. These are some examples of atomic clocks that were first fabricated on a chip scale back in 2004 by NIST. These set a trend of miniaturization for other sensors. Later, a few years later, these became commercially available. Less than 10 years later, they were commercially available, and their performance is almost 1,000 times better than their counterparts, quartz oscillator or WIMS oscillator. They have many applications, including civil and military applications, including jamming and navigation, as well as civil like communication and for future maybe the autonomous vehicles. Atomic magnetometers work on a similar principle. However, over here we have two differences. Basically, the reference oscillator is used to modulate the magnetic field instead of the laser wavelength, and we don't have a shielding for these sensors because it needs to be exposed to external fields. And finally, detection. And we can see here some of this is like a typical output of these kind of atomic magnetometers, and with a small enough applied field, we can have a fairly linear output. This is an example also by NIST, where they were able to demonstrate these sensors on a small scale, and with extremely high performance that is on the order of femtotesla range. This is 1 billion times smaller than the Earth magnetic field. So all this miniaturization and high performance led this kind of sensor to become commercially available. These are available right now, and many throughout the literature are trying to use them for applications like medical imaging. Brain waves, they have magnetic field associated with them, and there are many publications people are trying to use them. One notable and recent publication, people have tried to use these sensors and comparing them to traditional or like conventional MRI machines. However, and the results were comparable on the same order of magnitude. We can all imagine that if you can have this kind of extreme accuracy without the need for helium cooling or the huge magnets that's inside this machine, this will enable so many applications that we are not aware of today. I would like the third example, and that's what I'll be closing my talk about, is the atomic gyroscope. The atomic gyroscope is a little bit more complicated. As you can see from the scheme here, it has two laser beams perpendicular to each other. There are three magnetic field coils and a little bit more complicated electronics. Additionally, the alkali atoms that we used in our atomic magnetometers and clock doesn't work for gyroscopic motion. We need special atom species like xenon or helium to be used inside these devices. So we introduce additional atom species, and we're going to use alkali metals to be able to polarize them and prepare them, because as we all know, xenon and helium are inert gases that does not absorb light. So to simplify how these gyros work, let's imagine that each xenon atom is like this spin top we see here on the screen. If we were moving in a rotational manner, we can see that we can observe a different frequency of rotation of this kind of spin tops. So if we were, we in this gyroscope we synchronize all of these xenon atom to be in phase, and then we can detect their motion or their precession frequency using an atomic magnetometer. Luckily, we have an alkali metal in our cells, and we can use that for detection. As I said before, gyroscopes are quite complicated than magnetometers and clocks. There is no commercial product for this, but there are some quite impressive work that was done in our lab in UCI. The top design we see here, an atomic cell with integrated reflectors and the optical bench that have the VCSEL and the light detectors made in a separate chip. On the bottom here, we see another design that I personally worked on during my PhD, where we used the silicon as a structural material, and we used polymers like perylene C and polyamide to be able to fold these in a 3D structures. And we made most of these components made of using microfabrication techniques. To give completion of to the picture, I would like to mention also there are advanced prototypes of these kind of sensors by Northrop Grumman in the United States. However, these sensors, although they are extremely, they have extreme performance that's reaching the navigation grade for gyroscopes, these are made using conventional methods and pick and place, as you would say. And with that, this is the end of my talk. I would like to just give 3 remarks in the conclusion. Similar to what we have in the 1990s when gyroscopes came, the MEMS gyroscopes came. Nobody was thinking they will be in our phones, inside our pockets. New application will emerge for these kind of sensors. Further development is required to make them cheaper and they can spread wider. And although there are some limitation in these sensors, but we are far away from the theoretical limitation, and more technological advancement is required to improve their performance. And thank you.
Good afternoon. So that was the last session of the Future of Semiconductor Forum. I would like to thank you for your attending, and I would like also to thank our speakers for the sharing of their work and for the sharing of the knowledge as well. So now I will open the floor for the questions from the audience. Yes. Dr. Saad. Mike.
Yes, I have 2 questions, one for Prof. Khalid and the other one for Dr. Nazek. Prof. Khalid, just wanted to ask the material that has been used for the magnetic skin, and also the methodology that the glass work in detecting the signal. Is it a magnetic field? Do they detect a magnetic field, or is there any other way of communication or other signals?
So regarding the sensors, these are the regular sensors that detect the magnetic field. And what happens is that when the material deforms, the magnetic field changes. So we are monitoring the change in the magnetic field. And we use multiple of them because we are actually trying to explore the differences between left and right. So that's one thing. The magnetic materials, we are using a type of iron, and we're casting that with EcoFlex just to provide a substrate and flexibility.
Dr. Nazek, I have like one question of 2 parts. The first part, when you mentioned about the cubic mix of sensors, and you said like when we throw it in the water, it adjusts itself. Is it like kind of gyroscope or something related to gravity?
Yes, exactly. So it's gravity. So by so by encapsulating this cubic system using the PDMS, we actually encapsulated it in an asymmetric way to change the center of gravity of the system so that when it's thrown into the water, it will rotate and self-adjust its position, so that the face with the water quality sensors is always in contact with the water, while the face with the solar cell is always facing the sun.
The last question is for the project that you mentioned with the Lockheed Martin. You mentioned that the flexible solar cells managed to extend the life of the battery for drones. Do you have like a figure of like percentage?
Exactly. So currently, I wouldn't say this is the optimized version. We were able to extend by 10%, but this is not the optimized version. We're still hoping and expecting to improve this performance. And the reason is that usually you need a power management chip in between the solar cells and the batteries of the drone. And these power management chips, we did not design them or fabricate them ourselves. We got chips which are off the shelf. So they had a specific efficiency and they were not really optimized to our application. So this is why it limited the overall extension of the flight time.
Yeah, any other question? Yes, please.
First of all, thank you all for very rich presentations. They were actually very amazing. So my question is to Dr. Sahika. Can you shed light on, if there is a work field that's focusing a lot on early detection of cancerous cell? I remember I was working on this, I was doing research on this field around 2019, and there was a huge research, but there wasn't actually a sensible product that we can use. If you can shed light on this field in general, and when do you expect to see something that will work?
Right. Thank you for the question. Yeah, I mean, cancer is one of the biggest problems, and people do want to make a sensor for early detection of cancer. But as terrible it is, cancer is also a very diverse disease. Therefore, the biomarkers of cancer are various, and they do even change from person to person. Therefore, making one sensor only for maybe one biomarker is easy. But the idea is to be able to find multiple biomarkers, but those biomarkers also do not emerge early enough. Like a patient, obviously, who's at maybe like stage 3 or 4, you may find in the blood several of these biomarkers, but unfortunately not for the early stage.
Yeah. Do we have any other questions? Okay, Professor Salama, you have mentioned that the gas sensing and the application of nitrogen dioxide sensing. So you have used the blue LED instead of the UV, for example. Yeah. The question is, what is the advantage in this case? I mean, the cost is basically the main thing. But if we ignore the cost, what we will have?
No, I mean, if we ignore the cost, then I'll go for the UV if it's available and it's readily used. But the good thing about the blue UVs is that they are readily available. So you could actually just buy them, I mean, in bulk, and put them in the system. They don't cost too much power. So that's also a big advantage, that because the system has to run on a battery. So, and you have to do, every time you are doing a measurement, you have to do a reset operation. So, and it's part of the calibration process. So using the UV. Now, the drawback is that you have to wait for a longer period of time for reviving. So instead of, for the UV is from 1 to 2 minutes. For the blue one, it's 5 to 10 minutes in order to achieve full revival.
Okay, thank you. With that, we conclude our session. Thank you so much. Yeah, do you have any? Yeah.
Professor Khalid. So, actually, I have a question on your gas sensor. So, can you please elaborate and give us actually the way of resetting your sensor?
So, the way of resetting goes like this. So, when you have the nitrogen dioxide attached to the indium on the channel of your transistor, it's a very strong bond. So it has been observed that when you actually shine UV on it, typically there are two types of revival. Either you use high temperature, so you heat your sensor, and this is not feasible for any handheld device because it consumes a lot of power. The other one is actually using UV, and you shine UV, and that manages to break the bond there, and then the molecules can escape. The problem with that is that UV is not as easy and it's not as cheap as to find compared to the blue LEDs, which is readily available.
And nothing happens to the channel?
What?
Nothing happens to the channel material when you
No.
shine UV?
No, nothing. I mean, like it's, no.
That's great. Okay, I think we have 2 minutes, so if we have any questions. Yeah. Okay, thank you so much. Thank you again for attending, and thanks for our speakers.
Now, with the closing ceremony, may I ask all of you to please welcome Dr. Saeed al-Shihri.
So here we come to the end. It has been truly 2 great days. I would thank you all actually for attending this forum organized by the Research, Development and Innovation Authority along with CACS and KAUST. I would thank our distinguished speakers, and also I would thank our researchers and students who participated in the poster sessions. I would thank our sponsors for their great contribution, and I would also thank the organizers who did a great job in making this event happen. I would thank 2 of my colleagues actually who did start planning and do in the beginning, Professor Lee and Dr. Ma Khayyat and other colleagues, Dr. Ahmed, Dr. Abdullah Al-Harbi, Dr. Abdullah Al-Hassan, Dr. Salman Al-Faid, and all other colleagues. I would thank Abu Mansour, Muad Al-Tamimi and his team for the great organizing and making all what you've seen now, real. So with that, I would thank you all, and I would invite you to attend the next forum at KAUST next year. Thank you very much.
Thank you, Dr. Saeed. It is time for the awards, so may I ask Professor Shuji Nakamura on stage? And Professor Saeed. عبد الإله صالح